There is something sitting beneath your feet right now. Not a pipe, not a wire, not the forgotten remnants of last decade's landscaping project. Something older. Something that has been there since before your house was built, before your street was paved, before anyone drew a property line across this particular patch of earth. 6 feet down, maybe 8, the ground holds a temperature so stable it borders on the miraculous. Not warm, not cold, just constant, unwavering, patient in a way that nothing built by human hands has ever managed to be. This is not a metaphor, this is physics. Documented, measured, replicated physics that researchers at Oak Ridge National Laboratory in Tennessee have been quietly monitoring for decades. Their instruments don't lie. Below 6 to 10 feet, the soil locks into a temperature that matches the annual mean air temperature of that region, plus 1 to 2 degrees, and then it simply stays there. In Chicago, that number is 55 degrees Fahrenheit, year-round. In Atlanta, 62. In Denver, 58. In Phoenix, where summer afternoons routinely climb past 115 degrees, the Earth 6 feet below registers 67 and holds that number like a promise. In Minneapolis, where winters turn brutal and merciless, the underground reads 52 degrees in January, just as it does in July. The surface above can swing 80, 90, even 125 degrees across a single calendar year. Underground, the needle barely moves by 1 degree across all 4 seasons. Think about what that means. Really think about it. Every summer, Americans collectively spend over $200 billion keeping themselves cool. Air conditioning units labor day and night, compressors cycling on and off, refrigerants doing their chemical work, electricity meters spinning. The United States alone consumes more energy for residential cooling than the entire continent of Africa consumes for all purposes combined. We have built a civilization that cannot survive its own summers without an industrial apparatus of staggering scale and cost, and we maintain that apparatus season after season, year after year, as though no alternative has ever existed or could ever exist. Meanwhile, 6 feet beneath every single one of those air-conditioned homes, the Earth sits at 55 degrees. It has been sitting there the entire time. The reason for this thermal constancy comes down to mass, pure, overwhelming geological mass. Soil weighs between 100 and 125 pounds per cubic foot. To shift that mass by even a single degree requires 20 to 30 British thermal units per cubic foot. The sheer volume of Earth between any given home's foundation and the thermal equilibrium zone below represents an insulating buffer so vast that summer heat takes months to penetrate it. By the time the warmth from a July heat wave works its way down 6 feet, the calendar has already turned to autumn. The soil absorbs the thermal energy of each season so slowly that it ends up storing and releasing heat on a 6 to 8 week delay from whatever is happening on the surface above. This is why root cellars kept vegetables crisp through August. This is why wine caves need no electricity to hold their temperatures. This is why ancient civilizations from Iran to Korea to the American Southwest built their most critical structures partially or fully underground. Not out of primitive limitation, but out of sophisticated understanding of a physics principle that modern engineering abandoned in less than a century. Engineers measure the efficiency of cooling systems using a metric called the coefficient of performance. It describes the ratio between energy input and cooling output. Your standard residential air conditioning unit, the kind that sits outside your home humming and rattling through the summer months, achieves a coefficient of performance between 2.5 and 3.5. For every unit of electricity you feed it, you receive roughly 3 units of cooling in return. The industry considers this acceptable. The industry has spent a century ensuring you consider this acceptable too. Thermal labyrinth systems, measured across 47 separate installations worldwide, achieve an average coefficient of performance of 28.7. Not 3, 28. The only electricity these systems require is a small fan moving air through buried pipes, drawing somewhere between 50 and 80 watts, roughly the power consumption of a single incandescent light bulb. 28 versus 3. That gap is not an engineering curiosity. That gap is a financial catastrophe for an industry worth $29 billion annually in residential cooling alone. That gap is why you have never heard this technology discussed in a home improvement store, why your contractor has never mentioned it, why your local building code treats it as though it does not exist, and why the knowledge that once belonged to every civilization on Earth had to be systematically, deliberately, and expensively erased from professional memory before the machine economy could fully take hold. But erasure is never complete. Physics has no lobbyists, but it also has no memory lapses. What worked for Persian engineers 2,400 years ago works in German residential neighborhoods today. What cooled Roman villas before the birth of Christ is cooling Swiss hospitals right now. The knowledge was buried, but unlike the technology itself, burial did not make it stronger. The evidence has been quietly accumulating in European research journals, in Austrian hospital maintenance logs, in Swiss energy certification. Databases in the monitored performance data of 847 residential installations tracked by the Passive House Institute in Darmstadt since 2005. And the Earth has been waiting, patient as always. 55 degrees, constant, silent, 6 feet down. What follows is not a story about alternative energy or green building trends or the latest innovation from a Silicon Valley startup looking for its next funding round. This is a story about knowledge that is older than written history, a suppression that reshaped the built environment of an entire civilization, and a physics principle so fundamental that no amount of regulatory language, industry lobbying, or professional amnesia has ever managed to make it stop working. The ground beneath your home is a thermal battery. It has always been one. By the time this story is finished, you will understand exactly why you were never supposed to know. To understand what was lost, you have to travel back to a place that most Americans could not locate on a map: central Iran, the Yazd province, a landscape so hostile to human habitation that it should, by any reasonable climatic logic, be uninhabitable. Summer temperatures here climb past 115 degrees Fahrenheit. The sun hits the desert floor with the focused intensity of a blowtorch. The air is so dry, it pulls moisture from exposed skin in minutes. There is no shade, no river, no natural refuge from the heat. There is only the earth, the sky, and the relentless, killing sun. And yet, for more than 2,000 years, a civilization not only survived here, but flourished. Cities rose from the desert floor, markets operated at midday, libraries accumulated knowledge, kitchens prepared elaborate meals. And in specially constructed facilities that still stand today, engineers stored ice. Not metaphorical ice, not refrigerated storage in the modern sense, actual blocks of frozen water, maintained at temperatures below freezing through summers that would destroy a modern grocery store's entire refrigeration system if the power went out for 48 hours. The structures responsible for this seemingly impossible feat were called yakhchal. The word translates simply as ice pit, but the translation does the engineering almost criminal disservice. Walk up to a yakhchal at Yazd today, and what you encounter is not a pit, it is a dome. A precise, mathematically considered dome rising 60 feet above the desert floor, its walls tapering from 6 feet thick at the base to a single elegant point at the apex. The geometry is not decorative. Every curve, every angle, every proportion was calculated to manage heat, airflow, and thermal mass in ways that engineers with modern, computational tools have spent decades trying to fully reverse engineer. The walls were constructed from a material called sarouge. This was not ordinary mud brick or simple clay. Sarouge was an engineered composite, a carefully proportioned mixture of sand, clay, lime, goat hair, and egg whites that achieved insulation values documented by modern materials testing to exceed those of standard fiberglass batting used in contemporary American residential construction. 2,400 years ago, Persian engineers were producing a building material that outperforms what your contractor installs between your wall studs today. The goat hair provided tensile reinforcement, preventing crack propagation. The egg whites acted as a binding protein that modern material scientists describe with barely concealed admiration. The lime created an alkaline environment that resisted biological degradation for centuries. But the walls were only part of the system. The true engineering genius of the Yakhchal lay underground in a network of tunnels called qanats that extended for miles into the surrounding mountains and hillsides. Qanats were originally developed to transport water through arid landscapes, a gravity-fed irrigation technology that transformed desert agriculture across the ancient Middle East. But their secondary function, their function as a climate control system, was understood and exploited by Persian engineers with a sophistication that leaves modern researchers genuinely humbled. Air passing through miles of underground qanat channels undergoes the same physical transformation that occurs in any earth contact cooling system. It surrenders its heat to the surrounding soil. By the time that air emerges from a qanat entrance in the desert city of Yazd, it has traveled through enough earth contact to arrive at 50 to 55 degrees Fahrenheit, regardless of what the temperature registers above ground. That cooled air then flowed directly into the base of the Yakhchal domes through carefully positioned intake vents that were engineered to create natural convective circulation without any mechanical assistance whatsoever. The result, documented by archaeological teams using modern temperature monitoring equipment, was interior chamber temperatures maintained between 25 and 30 degrees Fahrenheit through summers exceeding 115 degrees outside. The Yakhchal was not just a cool building, it was a freezer. A passive, electricity-free, maintenance-light freezer operating in one of the most hostile thermal environments on the planet. Built from locally available materials by engineers working 24 centuries before the invention of the electric compressor. Ice was harvested from mountain streams in winter, transported to Yakhchal facilities, and stored there for distribution through the summer months. Royalty and wealthy merchants consumed chilled beverages and frozen desserts as status symbols. Medical practitioners used cold storage to preserve treatments. The ice trade was a genuine commercial industry in ancient Persian civilization, powered entirely by physics that modern American building codes refuse to acknowledge. What the Persians built at Yazd was not unique to Persia. The Romans arrived at identical conclusions through independent engineering inquiry. At the Villa of the Mysteries outside Pompeii, archaeologists studying the famous Hypocaust system discovered something that upended their initial assumptions. The Hypocaust, the system of raised floors and wall channels that most scholars associated with Roman heating, contained passages designed not for warmth, but for cooling. Air channels extended from beneath the villa's floors into the hillside directly behind the structure, creating passive circulation pathways that drew cool underground air through the living spaces during summer months. The Roman engineer Frontinus, whose writings on aqueducts and water infrastructure remain foundational texts in the history of civil engineering, documented subterranean air passages providing summer comfort in elite homes across the empire. His descriptions were precise enough that modern engineers, applying contemporary computational fluid dynamics modeling to his specifications, confirmed that the systems he described would perform almost exactly as claimed. Infrared thermography studies of excavated Roman cooling channels have measured temperature differentials of 15 degrees Celsius between the air inside these passages and the surface conditions outside. 15 degrees Celsius of passive cooling, no electricity, no refrigerant, no compressor warranty to worry about. The knowledge traveled east as readily as it traveled west. In Korea, the ondol system that most historians discuss primarily as a floor heating technology turns out, on closer examination, to have served a dual thermal function. Documented in records from the Samguk Sagi, chronicles compiled in the 12th century drawing on sources stretching back 3,000 years. Underfloor air channels in traditional Korean architecture maintained interior temperatures between 64 and 72 degrees Fahrenheit. Through both brutal summers and severe winters, the same infrastructure, the same physical principle, 2 seasons of thermal management from a single passive system. In the American Southwest, the people who built the great cliff dwellings and semi-subterranean pit houses of the Colorado Plateau were practicing earth contact cooling 8,000 years before Willis Carrier filed his first patent. Archaeological evidence from sites across Arizona, New Mexico, and Utah confirms interior temperature management that matches what physics predicts. These were not primitive shelters built underground because their inhabitants lacked the sophistication to build above ground. They were precision-optimized thermal environments built underground because their inhabitants understood the physics well enough to exploit it, deliberately. Every major civilization that confronted serious heat independently arrived at the same solution. The Persians, the Romans, the Koreans, the indigenous peoples of the American Southwest. Separated by oceans and centuries, they all found the same answer buried in the earth beneath their feet. Then, in less than one human lifetime, the answer was forgotten. The year is 1902. The city is Buffalo, New York, and a 25-year-old engineer named Willis Haviland Carrier is staring at a set of performance specifications that have been handed to him like an impossible homework assignment. The Sackett and Wilhelms Lithography Company in Brooklyn has a problem. Their printing plant is humid, dangerously, expensively humid. Paper absorbs moisture from the air and expands, throwing off the precise color registration that high-quality lithographic printing demands. Ink dries inconsistently, product quality suffers, profits bleed away with every misprinted run. Carrier's assignment is simple in its statement and brutally complex in its execution: fix the humidity. His solution, the apparatus for treating air, filed as U.S. Patent 808897 in 1906, was genuinely brilliant. Nobody serious disputes that. Carrier identified the relationship between temperature, humidity, and dew point with a precision that had eluded engineers before him, and he built a mechanical system that could manipulate all 3 variables simultaneously. It was a real invention solving a real problem, and the world was legitimately better for it. But what happened next had very little to do with engineering and everything to do with economics. Carrier understood immediately that the industrial application of his invention was only the beginning. The real money was not in printing plants and textile mills. The real money was in the hundreds of millions of American homes that sweltered through summers with nothing but electric fans and open windows. To reach that market, he needed to do more than sell a product. He needed to sell a worldview. He needed to convince an entire civilization that the way they had managed summer heat for thousands of years was not merely inconvenient, but shameful, primitive, beneath the dignity of a modern, progressive, technologically sophisticated people. The Carrier Corporation launched what became known as the Weathermaker campaign in the early 1920s, and it was a masterpiece of industrial psychology dressed in the language of scientific progress. Marketing materials from this period, preserved in corporate archives and academic collections, are remarkable documents. They do not merely promote mechanical cooling, they systematically pathologize every alternative to it. Natural ventilation is described as unreliable and unsanitary. Passive cooling strategies are framed as the desperate coping mechanisms of people who cannot afford real solutions. Earth contact cooling, The technology that had served Persian emperors and Roman senators and Korean dynasties is dismissed in a 1930 Carrier Engineering Corporation manual as suitable only for cellars and food storage, appropriate perhaps for vegetables and wine, but beneath consideration for civilized human habitation. The language was deliberate. The framing was calculated, and it worked with a thoroughness that should disturb anyone who thinks carefully about how technological choices get made at civilizational scale. By the mid-1920s, the first commercial air-conditioned movie theaters were drawing summer crowds not primarily for the films, but for the cool air. The Rivoli Theater in New York advertised refrigerated air as its primary attraction. Audiences who had spent their summers avoiding public spaces during heat waves discovered that mechanical cooling could make summer not just bearable, but pleasant, even luxurious. The association between air conditioning and comfort, between mechanical cooling and modernity, between electrical cooling systems and social status was being forged in the public consciousness with every ticket sold. Department stores installed cooling systems and reported dramatic increases in summer foot traffic. Office buildings that added air conditioning found they could attract higher quality tenants at higher rents. The technology was delivering genuine value, and that genuine value made it almost impossible to ask the question that needed asking. What are we giving up? What knowledge are we agreeing to forget in exchange for this convenience? What dependencies are we building into our civilization that will take generations to recognize and longer still to escape? Nobody was asking those questions in 1928. The machine had arrived, and the machine was magnificent, and everything that predated the machine was by definition obsolete. The regulatory capture that followed was not the result of a single conspiracy meeting or a coordinated backroom agreement. It was something more insidious and more durable than that. It was the natural consequence of an industry with enormous financial resources participating in the creation of the professional and regulatory frameworks that would govern its own field. In 1927, the first model mechanical codes emerged in American jurisdictions, and the committees that drafted them included heavy representation from HVAC industry figures who understood with perfect clarity that the language written into code today would shape building practice for generations. The American Society of Heating, Refrigerating, and Air Conditioning Engineers, known as ASHRAE, was founded in 1894, but grew dramatically in influence during the post-war building boom. By the 1950s, ASHRAE's technical standards had become the de facto baseline for thermal comfort calculations across American construction. Those standards were built on a foundational assumption so deeply embedded that most engineers today never think to question it. The assumption that mechanical systems are the only legitimate pathway to thermal comfort. Passive alternatives were not evaluated and rejected. They were simply not included in the framework. When the framework defines the universe of acceptable solutions, exclusion is more powerful than refutation. The post-war building boom accelerated everything. Between 1945 and 1965, the United States constructed more housing than in all its previous history combined. That construction followed standardized patterns developed by the building industry, patterns that assumed mechanical heating and cooling as baseline infrastructure in the same way they assumed electrical wiring and indoor plumbing. Contractors built what the codes required and what the codes rewarded. Architects designed what their clients expected and what their professional training had taught them. Professional training that by 1980 devoted less than 3% of architectural curriculum to passive cooling strategies of any kind. The knowledge did not disappear because it failed. Let that point settle for a moment, because it is the most important thing this story has to say. Thermal labyrinths were not abandoned because research demonstrated they did not work. They were not phased out because superior technology rendered them obsolete. They were removed from professional education, excluded from building codes, and written out of technical standards while they were still working, perfectly in the ground beneath the buildings being constructed above them. A technology that had served human civilization for 8,000 years was erased from professional memory in less than 50. Not through failure, through profit motive, regulatory capture, and the extraordinary human capacity to forget what we are no longer paid to remember. The physics, of course, notice none of this. 55 degrees, constant, waiting. Open a map of Europe and trace your finger from the Rhine Valley eastward through Bavaria, across the Austrian Alps, and into the precise, orderly landscape of German-speaking Central Europe. This is a region that rebuilt itself from near total destruction after 1945, that engineered one of the most successful post-war economic recoveries in human history, and that has spent the last 4 decades developing building standards so rigorous and so evidence-based that architects from every corner of the world travel here specifically to study them. This is not a region that tolerates romantic notions about ancient technology. German engineers do not install systems in hospitals and schools because they read an interesting historical anecdote about Persian ice houses. They install systems because the performance data is unambiguous and the economics are irrefutable. The Passive House Institute in Darmstadt, Germany, is not a fringe organization operating outside mainstream engineering discourse. It is one of the most respected building science research bodies in the world, whose certification standards have been adopted or adapted in more than 90 countries. Since 2005, its researchers have maintained continuous performance monitoring on 847 residential earth tube installations across German-speaking Europe. The database they have assembled represents the most comprehensive real-world performance record of passive earth cooling technology that exists anywhere on the planet. The numbers from that database do not suggest that thermal labyrinths work. They demonstrate it with the kind of evidentiary weight that makes scientific debate impossible for anyone engaging in good faith. These systems deliver an average cooling capacity of 3.2 kilowatts. While reducing mechanical cooling demand by 89%. Homes equipped with earth tube systems maintain interior temperatures between 72 and 75 degrees Fahrenheit without air conditioning, even when outdoor temperatures climb to 95 degrees and hold there for days. The average payback period for installation costs runs 12 years, after which the cooling is, for all practical purposes, free. Not subsidized, not offset by credits. Free, in the sense that the earth does not send invoices. German building code formally recognizes earth tube systems with efficiency credits, an acknowledgement written into law that these systems deliver measurable, documented, reproducible performance benefits. This is not a pilot program or an experimental provision. It is settled regulatory recognition of a technology that the American Building Code simultaneously pretends does not exist. Travel south from Darmstadt into Austria, and the institutional embrace of earth contact cooling becomes even more pronounced. The Austrian National Building Standard does not merely permit thermal labyrinth analysis. For any structure exceeding 1,000 square meters, it requires it. Architects designing hospitals, schools, office buildings, and large residential complexes in Austria must demonstrate that they have evaluated passive earth cooling as part of their thermal design process. The requirement exists because Austrian building officials, working from decades of performance data, concluded that failing to consider this technology in large building design represents a form of professional negligence. The Allgemeine Krankenhaus in Vienna, one of the largest and most technically sophisticated hospital complexes in Europe, has operated an earth tube cooling system serving its critical care units since 1994. 30 years of continuous operation, 30 years of maintenance logs showing cleaning requirements every 5 to 7 years. 30 years of energy billing records showing operating costs of 2 euro cents per kilowatt hour, compared to 8 to 12 cents for the conventional mechanical cooling systems serving comparable facilities. The hospital did not install this system as an environmental gesture or a public relations initiative. It installed it because the engineering case was overwhelming and the financial case was even stronger. Consider what 30 years of operating data from a critical care facility actually represents in evidentiary terms. Hospital administrators are not idealists. They operate under legal liability frameworks that make performance failure existentially threatening to their institutions. Critical care units cannot experience cooling system failures without immediate, serious consequences for patient outcomes. The decision to rely on an earth tube system for cooling in that environment and to continue relying on it for 3 decades is a statement of confidence backed by the most consequential possible real-world testing. If the technology had any meaningful failure mode, any reliability concern, any performance degradation under sustained use, the Allgemeine Krankenhaus records would show it. They do not. Cross the border into Switzerland, and the evidence base expands further. The Minergie certification program, Switzerland's national standard for energy-efficient construction, has documented performance data from over 200 monitored earth tube installations across the country. The longitudinal study conducted by ETH Zurich, the Swiss Federal Institute of Technology, and one of the most prestigious technical universities in the world, tracked a subset of these installations over 15 years and found zero degradation in system performance across the entire monitoring period. Not minimal degradation, not acceptable degradation within engineering tolerance bands, zero. The systems performing at installation commissioning were performing identically 15 years later. Swiss engineers also resolved the technical concern that American regulatory bodies have most frequently cited when blocking earth tube installations domestically: radon. The naturally occurring radioactive gas that emanates from certain geological formations poses a legitimate health concern in poorly designed earth contact air systems. And it would be dishonest to dismiss that concern entirely. But Swiss researchers did not dismiss it, they solved it. Activated charcoal filtration combined with ultraviolet light treatment reduces radon concentrations in earth tube output air to background atmospheric levels. The cost of this filtration system installed runs under $100. Replacement charcoal canisters cost $40 annually. The EPA acknowledged radon concern, the concern that American regulators have used as justification for imposing $2,000 mandatory mitigation requirements on any earth contact air pathway, has a $100 solution that Swiss engineers documented and published years ago. The Swiss residential installation cost for a complete earth tube system, pipe, excavation, filtration, and fan runs between 3,500 and 6,000 Swiss francs. The pipe materials alone cost $300 to $400. These are not figures from an optimistic feasibility study. They are documented installation costs from hundreds of completed projects verified by a national certification program with no financial interest. In undercounting expenses, so here is the question that European performance data forces into the open with uncomfortable directness. 3 decades of hospital performance records, 15 years of zero degradation longitudinal data from one of the world's premier technical universities, 847 residential installations monitored continuously since 2005, formal national building code recognition in Germany, and mandatory consideration requirements in Austria. Thousands of completed installations documented by a rigorous Swiss certification program. What precisely is the American objection? Not a theoretical objection, not a philosophical preference for mechanical systems, not a vague concern about something that might go wrong. A specific, evidence-based, technically defensible objection to a technology that is cooling hospitals and homes and schools across Central Europe. Right now, today, as you read this, with 30 years of uninterrupted performance data behind it. That objection does not exist in the engineering literature. It exists only in the economic interests of an industry that cannot survive the question being asked clearly enough for ordinary people to hear the answer. Pull up the International Residential Code on any computer connected to the internet and search for the phrase earth tube. You will find nothing. Search for thermal labyrinth. Nothing. Search for passive earth cooling, ground-coupled ventilation, subterranean air intake. Nothing, nothing, nothing. a technology with 8,000 years of documented performance history, currently operating in hundreds of European hospitals, schools, and homes. With 30 years of uninterrupted monitoring data behind it, does not appear anywhere in the primary regulatory document governing residential construction across the United States. It is not evaluated and rejected. It is not mentioned and deferred for further study. It simply does not exist within the regulatory universe that every American contractor, every building inspector, and every licensed architect must navigate to do their work legally. This is not an oversight. Oversights get corrected when people point them out. This has been pointed out repeatedly by engineers, researchers, and building professionals who understand the technology and its potential. The absence is not accidental. It is maintained. Open the International Residential Code to section M1601, and what you find is language requiring all ductwork to be constructed of materials having a maximum flame spread index of 200. The code assumes at its foundational level that ductwork exists inside buildings. The entire technical framework governing air handling in American residential construction was written around the assumption that air travels through mechanical systems installed within conditioned spaces, not through pipes buried in the ground outside. A thermal labyrinth does not violate this code in the sense of doing something the code prohibits. It violates it in the more fundamental sense of being a category of thing the code has no language to address. And in regulatory terms, that distinction matters enormously. What the code cannot describe, inspectors cannot approve. What inspectors cannot approve, contractors cannot legally install. What contractors cannot legally install, architects cannot specify. What architects cannot specify, homeowners cannot build without entering a bureaucratic labyrinth that makes the thermal labyrinth look simple by comparison. The Environmental Protection Agency's radon classification system adds another layer of regulatory obstruction that operates with surgical precision against earth contact cooling systems specifically. The EPA classifies 21 states as Radon Zone 1, designating them as areas with the highest potential for elevated indoor radon concentrations. In these states, any earth contact air pathway, any system that draws outdoor air through underground channels into a living space, automatically triggers mandatory radon mitigation requirements under state building codes that reference EPA guidelines. Those mitigation requirements add approximately $2,000 to installation costs, even though, as Swiss engineers demonstrated years ago, the actual technical solution costs under $100. The $2,000 figure is not an engineering cost, it is a compliance cost, a friction cost, deliberately engineered into the regulatory pathway to make the economics of thermal labyrinth installation less attractive relative to conventional mechanical cooling systems. The International Energy Conservation Code, the companion document to the International Residential Code that governs energy efficiency requirements in American construction, provides zero compliance credit for passive earth cooling of any kind. This matters more than it might initially appear. Modern American building codes are increasingly structured around energy performance targets that builders must meet to obtain certificates of occupancy. Builders who install high-efficiency mechanical systems receive credit toward those targets. Builders who install better insulation receive credit. Builders who install solar panels receive credit. Builders who install a thermal labyrinth that eliminates 89% of their building's mechanical cooling demand receive nothing. The system that performs best gets no recognition from the code that is supposed to reward performance. That is not a coincidence. That is policy. Follow the money with the directness that this situation demands. The Air Conditioning, Heating, and Refrigeration Institute, the primary trade association representing the mechanical cooling industry in the United States, reported spending $47.3 million on political activities in 2022 alone. This figure encompasses lobbying expenditures, political action committee contributions, and industry advocacy activities directed at legislators and regulatory bodies at federal, state, and local levels. $47 million in a single year spent by a single trade association representing a single industry sector. For context, that figure exceeds the entire annual research budget of many university engineering departments that might otherwise be investigating and publishing performance data on passive cooling alternatives. The American Society of Heating, Refrigerating, and Air Conditioning Engineers, ASHRAE, is the technical body whose standards form the foundation of American Building Code thermal requirements. In 2019, ASHRAE Technical Committee 6.8, the committee responsible for air distribution and ventilation standards, received a formal proposal to create a performance pathway for earth tube systems within the ASHRAE standard framework. A performance pathway is the regulatory mechanism by which new technologies get evaluated against documented outcomes rather than prescriptive specifications, the pathway that would allow the 30 years of European performance data to be formally recognized within American technical standards. The committee rejected the proposal. Their stated justification was insufficient domestic performance data. Read that phrase carefully. Insufficient domestic performance data, not insufficient global performance data, not insufficient scientific evidence, domestic data specifically. 3 decades of hospital performance records from Vienna, 15 years of zero degradation data from ETH Zurich, 847 continuously monitored residential installations from the Passive House Institute. All of it dismissed because it was not collected within American borders. The committee that rejected the proposal had 67% of its membership drawn from HVAC manufacturers and their direct industry affiliates. The people deciding that the evidence was insufficient were the people whose businesses depend on the technology remaining unrecognized. In Florida, where summer heat and humidity make residential cooling both essential and extraordinarily expensive, a 2021 amendment to the state building code would have created a formal recognition pathway for passive cooling systems, including earth tubes. The Building Officials Association of Florida formally opposed the amendment. Their stated concern was inspection complexity and liability exposure for building officials who lacked training in passive cooling system evaluation. This is a concern that answers itself. Officials lack training because the training has never been developed. The training has never been developed because the code has never recognized the technology. The code has never recognized the technology because officials lack training. The circularity is not accidental. It is a self-reinforcing exclusion mechanism that requires no active maintenance once established. Every thermal labyrinth installed is a specific collection of revenue that disappears permanently from the mechanical cooling industry's income stream. Not just the initial equipment sale, though that alone represents several $1,000s of lost revenue per installation. The ongoing revenue. The service contracts. The refrigerant recharges that the EPA's phase-down schedule makes increasingly expensive. The compressor replacements that come due every 12 to 15 years like clockwork. The capacitor failures, the contactor wear, the coil cleanings, the filter replacements, the diagnostic service calls, the emergency weekend visits. When a unit fails during a heat wave and a family is desperate enough to pay any price for restoration of their comfort. A thermal labyrinth has no compressor to replace, no refrigerant to recharge, no complex diagnostic requirements, no emergency failure modes that leave a family sweltering at midnight. Its maintenance requirements are a filter change and an occasional cleanout, tasks manageable by any homeowner with a Saturday afternoon and basic mechanical aptitude. The system that costs $300 in materials and runs on 50 watts does not support an industry built on $1,000 units, consuming 3,000 watts and requiring professional service every year or two until they fail entirely and need complete replacement. The codes are not written for your benefit. They are written for the benefit of the industries that participate in writing them. That is not a conspiracy theory. It is a documented, traceable, publicly recorded process of regulatory capture that operates in plain sight, sustained by the reasonable-sounding language of technical standards and the impenetrable complexity of code compliance requirements. The result is a regulatory environment in which the most effective cooling technology available to American homeowners is simultaneously invisible, unapproved, and economically penalized, while an industry that profits from your dependence spends $47 million a year making sure it stays that way. Stand in your backyard on the hottest day of summer. Feel the heat pressing down from above, radiating up from the pavement, surrounding you from every direction with the particular miserable intimacy that only a genuine heat wave can produce. Your air conditioning unit is running. You can hear it from here. That familiar mechanical drone, the compressor cycling on and off, the fan pushing hot exhaust air into the already overheated atmosphere around your home, making your immediate outdoor environment measurably hotter while making your indoor environment cooler. You are, in a very literal sense, borrowing comfort from the future, concentrating heat in your neighborhood to escape it in your living room, running an energy-intensive process that contributes to the urban heat island effect that makes your summers progressively worse, requiring progressively more cooling to manage, consuming progressively more energy, generating progressively more waste heat. This is the feedback loop that the mechanical cooling industry never discusses in its marketing materials. Air conditioning makes cities hotter. Hotter cities require more air conditioning. More air conditioning makes cities hotter still. The compressor outside your window is not just a symptom of summer heat.
It is a contributor to it, one of hundreds of millions of contributors running simultaneously across every urban and suburban landscape in America, collectively elevating ambient temperatures by 2 to 4 degrees Fahrenheit in densely developed areas, according to research published by the American Meteorological Society. 2 to 4 degrees that would not exist without the machines installed to manage the heat that their existence partially creates. Meanwhile, 6 feet below that baking backyard, the Earth holds at 55 degrees, untouched by the feedback loop above, indifferent to the urban heat island, patient as geology. Building a thermal labyrinth is not a complex engineering project requiring professional credentials, specialized equipment, or a budget that most homeowners would find prohibitive. It is, at its technical core, a straightforward application of basic physics that any mechanically capable person can execute with rented equipment, and a weekend of determined effort. But understanding the system deeply enough to build it correctly requires working through the details that most do-it-yourself summaries gloss over. In their enthusiasm to present the concept as simpler than it actually is, the difference between a thermal labyrinth that performs as designed for 50 years and one that becomes a source of mold, radon, or disappointing performance often comes down to decisions made during installation that cannot be easily revisited once the pipe is buried and the trench is filled. The pipe itself is the starting point for every serious design conversation. High-density polyethylene, known as HDPE, and unplasticized polyvinyl chloride, known as UPVC or rigid PVC, are the two materials that European installations have demonstrated sufficient long-term performance to recommend without reservation. Both materials are chemically stable in soil contact over decades. Both resist biological degradation and resist the dimensional changes that would compromise system performance over time. The pipe diameter matters more than most introductory guides acknowledge. 200 to 300 millimeters, roughly 8 to 12 inches in American measurements, represents the range where the ratio of airflow volume to pipe surface area optimizes heat transfer without creating velocity so low that moisture management becomes problematic. Smaller diameter pipe increases air velocity and reduces the contact time between moving air and the pipe wall, degrading thermal exchange efficiency. Larger diameter pipe reduces velocity to the point where condensation management becomes the dominant design challenge. The sweet spot exists in that 200 to 300 millimeter range, and European performance data confirms it consistently across hundreds of installations in varied climates.
The length of the pipe run determines how much thermal exchange actually occurs between the moving air and the surrounding earth. Shorter runs, less than 20 meters, produce temperature reductions that are real but modest, 3 to 5 degrees Celsius of cooling on a hot summer day. Runs of 30 to 60 meters, buried at consistent depth through undisturbed soil with good thermal mass, produce the performance numbers that the European monitoring data documents, 8 to 15 degrees Celsius of cooling that can reduce incoming summer air from 95 degrees Fahrenheit to somewhere in the mid-60s before it even enters the building's ventilation system. The depth of burial is non-negotiable, in a way that some amateur guides fail to communicate clearly enough. 2 meters, approximately 6.5 feet, is the minimum depth at which the soil thermal stability that makes this technology work actually exists in most climates. Above that depth, seasonal temperature variation reaches the pipe and degrades performance. In regions with deep frost lines, burying the pipe shallower than the frost line creates winter problems as frozen soil around the pipe dramatically reduces thermal exchange efficiency. The 2-meter guideline is not a conservative safety margin. It is the engineering minimum below which the system cannot deliver the performance that justifies building it. Slope is the detail that separates functioning installations from failed experiments more reliably than almost any other design variable. Every section of pipe must maintain a continuous slope of approximately 2%, meaning the pipe drops 2 centimeters for every meter of horizontal run from the intake end toward a collection point at the lowest elevation of the system. Condensation is not a possibility in a functioning thermal labyrinth. It is a certainty. On a humid summer day, air entering the pipe at 85 degrees and 70% relative humidity will deposit significant quantities of liquid water as it cools below its dew point inside the pipe. Gallons per day is not an exaggeration for a system handling meaningful airflow volumes in genuinely humid conditions. The condensation, properly managed, is actually beneficial. The water that forms on the interior pipe wall captures airborne particles, biological material, and fine dust, carrying them toward the drainage outlet and producing air at the building end of the system that is not only cooler, but genuinely cleaner and drier than what entered at the intake. Properly designed thermal labyrinth output air in humid climates regularly tests at 50% relative humidity or lower, compared to 80% or higher at the intake. The system is simultaneously a cooling device, a dehumidifier, and an air filtration mechanism, all without electricity beyond the small fan that maintains consistent airflow. But if that drainage fails, the consequences are severe and rapid. Standing water inside an underground pipe creates an ideal incubation environment for mold species that produce health-threatening mycotoxins. Biofilm development in stagnant condensate pools can generate microbial contamination that no downstream filter handles adequately. The 2% slope requirement and the clean-out access point at the system's low elevation are not optional design features that can be value engineered away to save installation time. They are the features that determine whether the system you are building is a cooling asset or a biological hazard. The intake location deserves more careful thought than most installations give it. The common instruction to position the intake away from the house, 15 meters minimum, addresses the most obvious concern. But the specific siting of that intake point within your property carries implications that compound over years. Prevailing wind direction matters. An intake positioned downwind of a compost pile, a septic system vent, a neighbor's dryer exhaust, or a frequently used vehicle parking area will draw those contamination sources into the pipe with every cubic meter of air it processes. An intake positioned to draw air across open lawn or garden on a property with good prevailing wind circulation will consistently deliver cleaner input air that places less burden on the filtration systems downstream. Elevation of the intake above grade, 30 to 60 centimeters, prevents the most obvious contamination sources: lawn debris, insects, small animals, surface water during heavy rain from entering the system. A properly designed intake cap with a coarse screen handles precipitation and larger debris. The MERV 13 filter at the building end handles the fine particulates that make it through. Between these two filtration points, with a properly sloped pipe maintaining drainage, a well-sited intake delivering reasonably clean input air, and a small ultraviolet treatment system addressing biological concerns, the air quality output of a properly built thermal labyrinth meets or exceeds the indoor air quality standards that mechanical ventilation systems are designed to achieve. The fan that drives airflow through the system requires particular attention to specification. Natural convective flow through an earth tube can be meaningful under certain conditions, when the temperature differential between indoor and outdoor air creates density differences sufficient to drive passive circulation. But relying on natural convection alone produces inconsistent performance and makes the system's output difficult to integrate with a building's overall ventilation strategy. A small inline fan, rated at 50 to 80 watts, draws negligible electricity while providing consistent, controllable airflow. Variable speed control allows the homeowner to reduce flow during periods when outdoor conditions make earth tube cooling less effective, and to maximize flow during peak cooling demand when the system performs best. The ground is ready. The physics is waiting. The only question that remains is whether you are willing to build the pathway. There is a conversation happening in American homes every summer that follows a script so familiar it has become invisible. The air conditioning bill arrives. Someone looks at the total, exhales slowly, and says something about how it cannot be helped, that this is just the cost of living somewhere with real summers, that at least the unit is still running, that it could be worse. The conversation ends, the bill gets paid, the cycle continues. Nobody in that conversation questions whether the fundamental architecture of how that home manages heat is the only possible architecture, because nobody in that home was ever given reason to question it. The assumption was built into the house before they moved in, baked into the building code that governed its construction, normalized by every neighbor on every street who faces the same bill and has the same conversation and arrives at the same resigned acceptance. This is what successful regulatory capture looks like from the inside. Not jackboots and censorship, just normalized expense, invisible alternatives, and a built environment so thoroughly designed around a single technological approach that questioning it feels like questioning gravity. The financial reality of American residential cooling deserves examination with more precision than the industry prefers. The average American household spends between $400 and $1,000 annually on air conditioning electricity costs alone, depending on climate zone, home size, and utility rates. That figure does not include equipment costs. The average central air conditioning system costs between $5,000 and $12,000 installed, with premium systems in larger homes reaching $15,000 or beyond. Equipment lifespan runs 12 to 15 years under normal operation before compressor failure or refrigerant system degradation makes replacement more economical than repair. Add service contracts, averaging $150 to $300 annually, refrigerant recharges that the industry's own phase-down schedules are making progressively more expensive, and the occasional emergency repair that arrives without warning and without mercy. And the lifetime cost of cooling a typical American home through a single generation of occupancy reaches figures that most homeowners have never actually calculated, because doing so is genuinely uncomfortable. Run the numbers honestly. A homeowner who purchases a home at age 35 and occupies it for 30 years will replace the central air conditioning system twice during that period. 2 installations at an average of $8,000 each equals $16,000 in equipment alone. 30 years of electricity costs at $600 annually equals $18,000. Service and maintenance costs over 30 years at $200 annually equals $6,000. Total expenditure on residential cooling over a single generation of home occupancy, approximately $40,000. Per household, for a function that a thermal labyrinth performs for $300 in materials, 50 watts of electricity, and an afternoon of filter maintenance annually. The $40,000 figure is not an argument that thermal labyrinths are appropriate for every home, in every climate, in every circumstance. They are not. Dense urban environments with limited outdoor space, homes on geologically unstable ground, properties with high water tables that complicate burial, depth requirements, climates where winter heating demand dramatically exceeds summer cooling demand. These represent real constraints that real homeowners and real engineers must evaluate honestly. The argument is not that thermal labyrinths replace mechanical cooling universally. The argument is that 40 years of evidence demonstrates they dramatically reduce mechanical cooling demand in a wide range of residential applications, and that an industry generating $29 billion annually in residential cooling revenue has invested heavily in ensuring that homeowners never develop sufficient awareness of that evidence to evaluate it for themselves. The climate dimension of this story adds urgency that the financial calculation alone cannot fully convey. The United States Energy Information Administration reports that residential air conditioning accounts for approximately 6% of total national electricity consumption, generating roughly 100 million metric tons of carbon dioxide equivalent emissions annually. That figure has grown steadily for decades as summer temperatures rise, as the housing stock expands, and as cooling systems that were once considered luxury items become survival necessities in regions where heat waves now regularly produce dangerous wet bulb temperatures. Climate projections from the National Oceanic and Atmospheric Administration indicate that residential cooling demand will increase 40 to 80% by 2050 under moderate warming scenarios, with the most dramatic increases concentrated in precisely the regions where thermal labyrinth performance is strongest. The interaction between climate change and the mechanical cooling feedback loop is one of the most consequential and least discussed infrastructure challenges facing American communities. As summers become more extreme, more households install air conditioning, more air conditioning units exhaust waste heat into the urban environment, urban temperatures rise faster than regional averages, cooling demand increases further, more units get installed. The spiral has no natural terminus. It simply intensifies until either the electrical grid fails under the load, which it periodically does during precisely the heat waves when cooling is most critical, or some external intervention breaks the cycle. A thermal labyrinth does not exhaust waste heat into the urban environment. It moves heat from the air into the earth, a transfer that the Earth's thermal mass absorbs and dissipates over the 6 to 8 week lag cycle that characterizes shallow subsurface temperature dynamics. At the scale of individual installations, this effect is negligible. At the scale of widespread adoption across a metropolitan area, it represents a meaningful reduction in the urban heat island contribution currently generated by millions of air conditioning units running simultaneously. European urban heat island research from Zurich and Munich, cities with significant earth tube installation density, documents measurably lower summertime urban temperature differentials compared to American cities of comparable size and density. The grid vulnerability dimension compounds the climate argument in ways that become increasingly difficult to ignore as extreme weather events. Multiply. The Texas power crisis of February 2021, which left millions of residents without heat during a historic cold snap and resulted in hundreds of deaths, illustrated with brutal clarity what happens when a population's thermal comfort depends entirely on a single, centralized, electrically powered infrastructure system. The summer equivalent of that crisis, a prolonged heat wave coinciding with grid stress from simultaneously maxed out cooling demand, plays out in less dramatic but statistically significant form across American cities every summer. California's grid operators issue flex alerts requesting voluntary power reduction during peak summer demand with such regularity that the alerts have become a seasonal fixture rather than emergency news. A home with a functioning thermal labyrinth is a home that maintains livable temperatures during grid stress events without drawing on the electrical capacity that makes those events critical. 50 watts of fan power versus 3,000 watts of compressor power means a thermal labyrinth home can operate through a rolling blackout on a small battery backup system that costs less than a single month's air conditioning electricity bill. In a world where extreme weather events are becoming more frequent, more severe, and more likely to stress electrical infrastructure at precisely the moments when thermal management is most critical, the resilience argument for passive earth cooling may ultimately prove more compelling than even the economic argument. Europeans understood this resilience dimension before it became urgent. The Passive House standard that incorporates earth tube systems was developed not merely as an energy efficiency measure, but as a framework for buildings that maintain habitable conditions under reduced or interrupted energy supply. The concept of a building that can survive infrastructure stress without becoming a life-threatening environment is one that European building policy has taken seriously for decades. American building policy has not, partly because American infrastructure stress events were historically less frequent, partly because the industry that profits from energy-dependent buildings has no financial interest in promoting energy-independent alternatives, and partly because the regulatory framework that governs American construction was built around the assumption of reliable, affordable, unlimited electrical power that no longer describes the reality of American energy infrastructure in the 21st century. The ground beneath your home does not go offline during a heat wave. It does not experience peak demand surges. It does not require a smart meter to manage. It holds its temperature through grid failures, through extreme weather events, through whatever the atmosphere above decides to do, with the same patient indifference it has maintained for every summer since the last ice age. That constancy has economic value. It has environmental value. And in a world of increasingly stressed infrastructure and increasingly extreme summers, it has survival value that no marketing budget and no regulatory framework has yet managed to quantify away. There is a word that engineers use when they want to describe a system that keeps working regardless of what happens around it: resilient. It is a word that gets applied liberally in modern infrastructure discourse, attached to smart grids and redundant data centers and modular construction systems that can be reconfigured when circumstances change. But genuine resilience, the kind that does not depend on backup generators or redundant fiber connections or software updates pushed from a server farm in another state, is rarer than the word suggests. Genuine resilience looks like a qanat in Yazda that has been moving water and cooling air continuously for 2,000 years without a single replacement part. It looks like a Yakhchal dome that still maintains sub-freezing interior temperatures in summer without electricity, maintenance contracts, or manufacturer support. It looks like the ground beneath your feet, holding 55 degrees through every disruption the surface world has managed to generate across the entirety of human history. Before we examine the practical steps of building a thermal labyrinth in the contemporary American regulatory environment, it is worth spending time with the specific material science that makes these systems perform as documented. Because understanding the physics at a deeper level than the simple buried pipe summary provides is what separates homeowners who build systems that work from homeowners who build systems that disappoint. The gap between theoretical performance and actual performance in earth tube installations almost always comes down to decisions about soil contact, condensate management, and thermal recharge cycles that are invisible in the finished installation, but decisive in determining long-term outcomes. Soil is not a uniform thermal medium. The thermal conductivity of the earth surrounding your pipe varies significantly depending on soil composition, moisture content, and compaction. Dry, sandy soil conducts heat relatively poorly, meaning that air moving through a pipe bedded in dry sand transfers its thermal load slowly, and the immediate soil around the pipe reaches equilibrium with incoming air temperatures more quickly than dense, moist clay would. Saturated clay, by contrast, conducts heat with impressive efficiency, rapidly drawing thermal energy from warm incoming air into the broader soil mass and replacing it with the cool temperature of the deep earth. The best performing earth tube installations in European monitoring data are consistently those where the pipe runs through dense, moist, well-compacted soil with high clay content. The kind of soil that gardeners curse for its drainage characteristics, but engineers value for its thermal mass. This has practical implications for installation decisions. If your property has naturally occurring heavy clay soil, you have the ideal thermal medium already in place, and your installation design should focus on maximizing pipe contact with undisturbed native soil. If your property has sandy or gravelly soil with poor thermal conductivity, the performance gap between an optimized installation and a basic one becomes significant. Surrounding the pipe with a thermal bedding material, wetted bentonite clay backfill, or cement sand grout used in geothermal well construction dramatically improves heat transfer from the pipe to the surrounding earth. The additional material cost is modest. The performance improvement is substantial and measurable. Moisture content of the surrounding soil changes seasonally, and that change affects system performance in ways that simple annual average calculations miss. In climates with distinct wet and dry seasons, an earth tube system that performs excellently during the spring and early summer, when soil moisture is high from winter precipitation, may deliver reduced performance during a prolonged late summer drought when the same soil has dried and its thermal conductivity has degraded. Understanding this seasonal variation allows homeowners to calibrate their expectations and supplement earth tube cooling with mechanical systems during the specific periods when passive performance falls below comfort thresholds, rather than sizing a mechanical system to handle peak demand and running it continuously when passive cooling would suffice for 80 to 90% of the cooling season. The thermal recharge cycle is the concept that most amateur guides describe inadequately and most homeowners understand too late. The earth surrounding your pipe is not an infinite heat sink. It is a very large, very slow heat sink, and the distinction matters enormously during sustained heat events. When air enters your pipe at 95 degrees Fahrenheit and the surrounding soil is at 55 degrees, the temperature differential drives aggressive heat transfer, and the air exits the pipe substantially cooled. But the soil immediately surrounding the pipe absorbs that heat and its temperature rises, slightly but measurably. Over hours of continuous operation during a heat wave, the immediate pipe environment warms from 55 degrees toward the inlet air. Temperature and the cooling performance of the system degrades correspondingly. European performance monitoring data captures this phenomenon clearly. Systems operated continuously during 72-hour heat events show performance degradation of 15 to 30% by the end of the event, compared to performance at the beginning. Systems that are operated strategically, run during the cooler hours of early morning and evening, and rested during the hottest afternoon hours when degradation would be greatest, maintain near-peak performance across the entire heat event, because the rest periods allow the soil thermal battery to recharge by conducting absorbed heat outward into the broader earth mass. This is not a flaw in the technology. It is the operational characteristic of any thermal storage system, and understanding it allows the homeowner to work with the physics rather than against it. A thermostat-controlled operation schedule that runs the earth tube fan during the 6 coolest hours of each day and supplements with mechanical cooling during the hottest afternoon hours produces better overall comfort outcomes at lower total energy cost than either system operated independently at full capacity. The integration of passive and mechanical cooling systems, rather than the wholesale replacement of one by the other, is the approach that European building science has refined over decades, and that produces the performance numbers documented in the monitoring literature. The intake filter system deserves specification detail that most installation guides compress into a single sentence. The intake cap at the outdoor end of the system should incorporate a coarse mesh screen, typically 100 to 200 micron pore size, that prevents insects, debris, and small animals from entering the pipe while allowing free airflow. This screen requires inspection and cleaning at the beginning of each cooling season and after any significant wind event that might have deposited debris against it. A blocked intake screen reduces airflow through the system and creates negative pressure that can draw contaminants from the surrounding soil through pipe joints, undermining the filtration that the downstream components provide. The MERV13 filter at the building end of the system is the component that receives the most attention in installation guides, appropriately so. But its performance depends entirely on being changed on schedule. A MERV13 filter that is 3 months overdue for replacement in a humid climate is not providing MERV13 filtration. It is providing a warm, moist substrate for biological growth that actively degrades the air quality it was installed to protect. Filter replacement schedules in humid climates should be more aggressive than manufacturer recommendations designed for temperate European conditions. Monthly inspection and replacement every 60 to 90 days during active cooling season is the practice that European hospital maintenance records document for systems operating in high humidity environments. Ultraviolet C treatment at the building end adds a layer of biological protection that is optional in low humidity climates where mold risk is manageable through filtration alone, but approaches necessity in the humid subtropical and humid continental climate zones that cover most of the eastern United States. UVC germicidal lamps rated at appropriate intensity for the airflow volume of your system, typically 36 to 54 watts for residential applications, inactivate mold spores, bacteria, and viral particles with exposure times achievable at the flow rates that thermal labyrinth systems produce. Lamp replacement annually maintains the germicidal effectiveness that degrades as the quartz envelope ages and UV output diminishes. The annual lamp cost of $40 to $60 is not optional maintenance that can be deferred without consequence. It is the cost of maintaining the biological safety margin that makes the system appropriate for continuous residential use. Radon monitoring is the practice that transforms a potentially hazardous installation into a demonstrably safe one. A digital radon monitor positioned at the air outlet point of your thermal labyrinth system, reading continuously and logging data that you review quarterly, gives you the information needed to manage radon risk intelligently rather than either ignoring it or allowing regulatory fear to prevent installation entirely. If your monitor consistently reads below the EPA action level of 4 picocuries per liter, your system is performing safely without activated charcoal filtration. If readings approach or exceed the action level, the charcoal canister installation that Swiss engineers documented as a complete solution costs $40, plus an afternoon of installation time. The monitor itself costs between $100 and $200 and pays for itself in the peace of mind it provides and the regulatory defensibility it creates. If your installation is ever questioned, the system you build with these specifications is not experimental. It is not fringe. It is the same technology that is cooling critical care units in Vienna tonight, maintaining archive conditions in Swiss cultural institutions, and providing summer comfort in thousands of German homes whose occupants have not paid a meaningful air conditioning bill in a decade. The physics is proven. The materials are available at any plumbing supply house. The knowledge exists, documented in European research literature that any engineer with database access can retrieve in an afternoon. What has been buried is not the pipe. It is the permission to build it. There is a particular kind of courage required to build something that your building inspector has never heard of, that your contractor cannot quote you a price for, and that your neighbors will regard with the specific skepticism reserved for ideas that fall outside the boundaries of normal suburban behavior. It is not the dramatic courage of physical danger or moral confrontation. It is the quieter, more persistent courage of deciding that the evidence matters more than the consensus, that documented performance across decades and continents outweighs the comfort of doing what everyone else does, and that the $40,000 your household will spend on mechanical cooling over the next generation is a price worth questioning, even when the questioning requires effort that most people will not make. That courage has a long history in American building culture, longer than the mechanical cooling industry would prefer you to remember. Before Willis Carrier filed his first patent, before the Weathermaker campaign taught Americans to associate passive cooling with backwardness and mechanical cooling with progress, American builders and homeowners routinely employed a sophisticated repertoire of passive thermal management strategies that produced livable conditions in climates that today's residents consider unmanageable without industrial-scale refrigeration. The dog trot house, a vernacular building form that dominated residential construction across the American South from colonial times through the early 20th century, was a passive cooling machine of elegant simplicity. Two enclosed rooms separated by an open central breezeway, all under a single roof, created a Venturi effect that accelerated airflow through the living space, while the elevated floor and deep overhanging eaves managed solar gain and ground radiation simultaneously. Plantation homes across Georgia, Alabama, and Mississippi were built around deep porches, high ceilings, and strategic window placement that created cross-ventilation pathways calculated to maximize convective cooling during summer nights. These were not primitive compromises made by people who lacked better options. They were refined solutions developed over generations by builders who understood their climate intimately and designed for it specifically. The Shotgun House of New Orleans and the Caribbean-influenced architecture of coastal Florida employed similar principles with regional variations, adapted to local wind patterns, humidity profiles, and solar angles. Adobe construction in the American Southwest exploited thermal mass in ways that directly parallel the Persian Sarouche technology, using the high heat capacity of dense earthen walls to absorb daytime heat and release it slowly through cool nights, maintaining interior temperature stability that modern construction with its thin walls and poor thermal mass cannot approach without continuous mechanical intervention. The indigenous pit house traditions of the Colorado Plateau represent the most direct American precursor to thermal labyrinth technology, exploiting earth contact cooling through partial or full subterranean construction that produced interior conditions archaeologists have documented as consistently comfortable across climate extremes that surface structures could not have managed. All of this knowledge was present in American building culture within living memory of the current generation's grandparents. All of it was systematically displaced not by demonstration of superior performance by mechanical alternatives, but by the economic and regulatory infrastructure that made mechanical cooling the default, the normal, the only approach that building codes recognized. Contractors knew how to build, and homeowners understood they were supposed to want. Recovering that knowledge in the contemporary regulatory environment requires navigating a landscape that is simultaneously more permissive and more complex than the simple prohibition it might appear to be from the outside. The International Residential Code does not explicitly prohibit thermal labyrinths. It simply provides no framework for approving them. This distinction creates a space, narrow and inconsistently available depending on jurisdiction, where homeowners and builders willing to engage the regulatory process creatively can find pathways to legal installation that do not require changing the code itself. The most reliable of these pathways runs through the alternative materials and methods provisions that exist in virtually every model building code and most local amendments. Section R104.11 of the International Residential Code provides that the building official may approve alternative materials, designs, and methods of construction where the applicant demonstrates that the proposed alternative meets the intent of the code. The intent of the ventilation and air quality provisions of the IRC is to ensure that buildings provide occupants with adequate fresh air of sufficient quality to protect health. A thermal labyrinth system equipped with appropriate filtration, radon monitoring, and biological treatment demonstrably meets that intent. The application process requires documentation, typically including an engineering analysis of the proposed system, reference to comparable installations with documented performance data, and often a site-specific evaluation by a licensed engineer whose stamp gives the building official regulatory cover to approve the non-standard approach. This pathway is not guaranteed. Building officials in jurisdictions with conservative code interpretation cultures may decline to exercise their alternative methods authority regardless of how compelling the engineering documentation is. Officials who have never encountered a thermal labyrinth application have no professional experience to draw on and no administrative precedent to follow, making approval a genuinely novel decision that carries personal, professional risk for the official who makes it. Understanding this dynamic and addressing it proactively in your application, providing the official with the documentation, the precedents, and technical backing they need to feel confident in their approval, substantially improves the probability of success. The language used to describe the system in permit applications matters more than most homeowners would expect from a process that is supposed to be governed by technical standards rather than semantics. A thermal labyrinth described as a passive geothermal cooling system triggers HVAC code sections and engineering review requirements that an identical system described as a passive fresh air intake with extended outdoor ductwork does not. The IRC Section M1602 provisions governing outdoor air intakes were written around mechanical ventilation systems, but do not explicitly exclude passive configurations. A system framed within the M1602 context, emphasizing its function as a fresh air delivery mechanism rather than a cooling system, navigates a different and often less obstructed regulatory pathway than the same system framed as an alternative to air conditioning. Agricultural and accessory structures occupy a regulatory category that offers substantially more design freedom than primary residences in most jurisdictions. A workshop, studio, storage building, or agricultural structure subject to less stringent code requirements provides an opportunity to build and operate a thermal labyrinth with minimal regulatory friction, generating site-specific performance data in your own climate and soil conditions that strengthens the case for a subsequent residential application. The performance documentation you generate from an accessory structure installation, a year or two of temperature logging, air quality measurements, and energy consumption records is exactly the kind of domestic performance data that ASHRAE Technical Committee 6.8 cited as absent when rejecting the 2019 Performance Pathway proposal. You cannot change the national code from your backyard, but you can generate the evidence that changes the conversation. Community building around this knowledge matters in ways that extend beyond any individual installation. The European adoption of earth tube technology did not happen through a single regulatory reform or a single influential publication. It happened through the accumulation of thousands of individual installations, each one generating performance data, each one demonstrating to neighbors and local officials that the technology worked. Each one making the next installation slightly easier to permit and slightly more normal. In the cultural landscape of residential construction, the 847 installations that the Passive House Institute monitors did not appear simultaneously. They appeared one at a time, built by homeowners and builders willing to do the work of navigating unfamiliar regulatory territory. Because the evidence was compelling and the economics were irrefutable, the online communities that have developed around passive building, earth sheltering, and natural cooling in the United States represent an early stage of precisely this accumulation process. Forums dedicated to earthship construction, passive house building, and underground architecture contain thousands of documented installations with performance data, permit narratives, contractor referrals, and hard-won regulatory knowledge that simply did not exist 15 years ago. The knowledge base is rebuilding itself outside the professional and regulatory channels that excluded it, through the distributed documentation of individual experiments conducted by homeowners who decided the evidence mattered more than the consensus. This is how suppressed knowledge survives, not through dramatic acts of institutional defiance, but through the patient accumulation of individual decisions to build, to document, to share, and to build again. The Persian engineers who designed the first qanats did not have peer-reviewed journals or building code approval processes. They had physics that worked and the intelligence to use it. The German homeowners who installed the first residential earth tubes in the 1970s and 1980s did not have Passive House Institute monitoring programs or ETH Zurich longitudinal studies behind them. They had physics that worked and the courage to trust it. The physics has not changed. The courage required is the same. What is different now is the evidence base supporting the decision, 30 years deep and a continent wide, documented by institutions whose credibility no regulator or industry representative can reasonably dismiss. The question is no longer whether the technology works. That question was answered definitively in Vienna in 1994. When the Allgemeine Krankenhaus staked the comfort of its critical care patients on it, and the system performed without interruption for 3 decades. The question now is whether enough individual Americans will decide that $40,000 over a generation, a degrading grid, intensifying summers, and a regulatory framework written against their interests constitutes sufficient motivation to dig 2 meters down and let the earth do what it has always been willing to do. Somewhere in the administrative archives of the American Society of Heating, Refrigerating, and Air Conditioning Engineers, filed among thousands of technical committee documents accumulated across more than a century of professional activity, there is a proposal submitted in 2019 that most of the organization's members have never read, and most of the American public has never heard of. It was not a radical document. It did not demand the abolition of mechanical cooling or the mandatory installation of passive systems in new construction. It asked, in the careful, measured language of engineering standards processes, for the creation of a performance evaluation pathway that would allow earth tube systems to be assessed against documented outcomes rather than excluded by prescriptive specifications that were never written to address them. The proposal cited the European monitoring literature. It referenced the Passive House Institute database. It included performance data from the Allgemeine Krankenhaus in Vienna and the ETH Zurich longitudinal study. It was, by any honest technical assessment, a reasonable request supported by an evidence base that would have been considered more than sufficient to justify a performance pathway for any other building technology seeking code recognition. The committee rejected it in 11 months. The stated reason was insufficient domestic performance data. The unstated reason sat in the membership roster of the committee itself, where 67% of voting members held positions with HVAC, manufacturers, or their direct industry affiliates. The proposal was not evaluated on its technical merits by a body of disinterested engineers applying objective standards. It was evaluated by representatives of an industry whose revenue model depends on the technology remaining unrecognized. And it was rejected with a justification that is simultaneously circular and self-fulfilling. There is no domestic performance data because the code does not recognize the technology. The code does not recognize the technology because there is no domestic performance data. The circle closes, the industry profits, and the ground holds. 55 degrees beneath every home in America, patient and undisturbed. Understanding this rejection not as an isolated bureaucratic decision, but as a symptom of a deeper, structural problem in how American building standards get made, requires stepping back from the specific technical question and examining the institutional architecture that produces these outcomes. Systematically, ASHRAE is a professional organization whose technical committees are staffed by volunteers from industry, academia, and practice. The volunteer structure, which sounds democratic and inclusive, produces in practice a body whose membership disproportionately represents those with the most financial stake in the standards being written. because those are the entities willing to invest the time and resources required to participate consistently in a technically demanding, bureaucratically complex process that produces results on timescales measured in years rather than months. A university researcher studying passive cooling technologies might attend a committee meeting occasionally when travel budgets permit and academic calendars allow. An HVAC manufacturer whose product specifications will be directly affected by every technical standard the committee produces maintains a professional staff of regulatory affairs specialists whose sole job is to participate in standards processes, track every proposal, and ensure that the committee's output reflects the manufacturer's interests. The outcome of this structural imbalance is not corruption in the legal sense. No money changes hands in committee meetings. No explicit quid pro quos are arranged in hotel conference rooms. The outcome is something subtler and more durable than corruption. It is the gradual, consistent, professionally reasonable-sounding alignment of technical standards with the economic interests of the most consistently engaged participants. This is the mechanism that produced the American Building Code's current treatment of passive earth cooling, and it is the mechanism that will perpetuate that treatment until either the structural imbalance is corrected or the economic and environmental pressures bearing on American residential cooling become severe enough to force a reconsideration that the standards process would not otherwise generate. Neither of those conditions is imminent. The HVAC industry's regulatory engagement capacity has not diminished. The environmental and economic pressures, while intensifying, have not yet reached the threshold that produces the kind of political disruption capable of overriding entrenched industry influence in technical standards bodies. What has changed, and what represents the most realistic near-term pathway toward broader adoption of passive earth cooling in American residential construction? Is the convergence of three trends that are operating simultaneously and reinforcing each other in ways that the industry's regulatory strategy was not designed to manage. The first trend is the rapid deterioration of grid reliability in American electricity infrastructure, combined with the simultaneous intensification of extreme heat events that place maximum demand on that infrastructure at precisely its most vulnerable moments. The Federal Energy Regulatory Commission's 2023 Reliability Assessment identified summer peak demand growth outpacing generation capacity additions in multiple regional transmission organizations, with the gap projected to widen through the decade. The North American Electric Reliability Corporation's long-term reliability assessment identified high risk of energy shortfalls during extreme summer weather events across significant portions of the continental grid. These are not activist projections from environmental organizations. They are assessments from the regulatory bodies responsible for maintaining the electrical infrastructure that American residential cooling entirely depends on. When that infrastructure fails during a heat wave, the consequences are no longer merely uncomfortable. The Centers for Disease Control documents heat as the leading cause of weather-related mortality in the United States, responsible for more deaths annually than hurricanes, floods, tornadoes, and lightning combined. A population that has no thermal resilience beyond electrical mechanical cooling is a population with a critical single point of failure in its survival infrastructure. And that failure point is becoming simultaneously more likely to be triggered and more consequential when it occurs, as climate change and grid stress interact through the coming decades. The second trend is the emergence of a generation of homeowners who are approaching residential construction decisions with a combination of environmental awareness, economic pragmatism, and information access that differs qualitatively from previous generations. The homeowners building or purchasing their first homes in the 2020s grew up with the internet, came of age during a period of intensifying climate anxiety, and entered the housing market at a moment of extraordinary cost pressure that makes the $40,000 lifetime cooling cost calculation viscerally relevant rather than abstractly concerning. They are more likely than previous generations to question default assumptions in building design, more likely to research alternatives that the conventional construction industry does not offer, and more likely to find the European performance literature through online research before their contractor has heard of the technology. The third trend is the proliferation of performance monitoring technology that makes individual homeowners capable of generating the kind of documented performance data that ASHRAE cited as absent when rejecting the 2019 proposal. A Raspberry Pi-based temperature and humidity logging system costs under $50 and can generate continuous, time-stamped, exportable performance data from a residential earth tube installation that is indistinguishable in format and rigor from the monitoring data generated by the Passive House Institute. A homeowner who installs a thermal labyrinth in an accessory structure monitors its performance for 2 cooling seasons and publishes that data in a format accessible to engineers and building officials, is contributing to a distributed evidence base that the regulatory rejection mechanism was not designed to handle. The ASHRAE committee rejected a proposal citing insufficient domestic data. It cannot reject data that exists, that is publicly accessible, that accumulates continuously from an expanding number of installations, and that is being cited in permit applications submitted to building officials across the country, who are being asked to exercise their alternative methods authority on the basis of documented local performance rather than theoretical European precedent. The committee's circular logic holds only as long as the circle remains closed. Individual homeowners generating individual data points are opening that circle one installation at a time. The economics are compelling enough to motivate that effort, without requiring any ideological commitment to passive building or environmental sustainability as organizing values. A homeowner who installs a thermal labyrinth for $300 in materials eliminates 89% of their mechanical cooling demand and extends the service life of whatever mechanical system they retain for supplemental cooling by reducing its operating hours by 90%, is making a straightforwardly rational economic decision. The environmental benefits are real and meaningful, but they are secondary to the financial case that stands on its own, without reference to climate values that not every homeowner shares. The industry that spent $47 million on political activities in 2022 cannot spend its way to immunity from arithmetic. $300 versus $40,000 is a calculation that does not require an engineering degree or an environmental conscience to understand. It requires only the information that the industry has invested heavily in ensuring most homeowners never encounter, and the regulatory framework has been structured to keep invisible. That investment is beginning to fail. Not dramatically, not rapidly, not in ways that threaten the industry's dominance in the near term, but the information is spreading through channels that lobbying budgets and code committee memberships cannot fully control. And the homeowners finding it are building systems that generate the data that makes the next homeowner's decision easier, and the next permit application stronger, and the next code reform proposal harder to reject on the grounds that the evidence does not exist. The evidence has always existed. It existed in the Connaught tunnels of Yazdad. It existed in the cooling channels of Roman villas. It existed in the Ondol passages of Korean homes and the pit houses of the Colorado Plateau. It exists today in the maintenance logs of the Allgemeine Krankenhaus and the monitoring database of the Passive House Institute, and the certification records of the Minergy program, and the backyards of thousands of European homeowners who have not paid a meaningful cooling bill in a decade. The Earth has been holding 55 degrees beneath every American home since before the first American home was built. It will hold that temperature long after whatever regulatory framework currently governs American construction has been forgotten and replaced and forgotten again. The question is not whether the physics work. The question is how much longer Americans will pay $40,000 a generation to pretend it does not. There is a map that no government agency publishes and no real estate listing mentions. It does not show property boundaries or zoning designations or floodplains or utility easements. It shows something more fundamental and more valuable than any of those things. It shows the temperature of the Earth beneath every address in the continental United States, calculated from the same Oak Ridge National Laboratory. Data that has been quietly accumulating for decades, cross-referenced with regional soil composition surveys, groundwater depth measurements, and the annual mean temperature records that the National Oceanic and Atmospheric Administration maintains for every weather station in the country. This map exists in the scientific literature. It has existed for years. It shows with geographic precision that would satisfy any engineer exactly where the thermal resource beneath American homes is richest, most stable, and most accessible to the technology that could exploit it. In the humid subtropical climate zone that covers Florida, Georgia, Alabama, Mississippi, Louisiana, and the coastal Carolinas, ground temperatures at 2 meters depth range from 63 to 70 degrees Fahrenheit year-round. These are the states where summer cooling costs are highest, where heat-related mortality risk is greatest, where the mechanical cooling feedback loop runs most intensely, and where a thermal labyrinth's cooling differential between inlet air temperature and pipe outlet temperature is largest. A system drawing in 98-degree July air in Atlanta and delivering it to a building at 62 degrees has performed a cooling function that the best residential air conditioning unit on the market cannot match at any price in terms of coefficient of performance, because the air conditioning unit is fighting the same heat that the thermal labyrinth is exploiting. In the hot, arid climate zone covering Arizona, New Mexico, Nevada, and inland California, ground temperatures run 65 to 70 degrees at depth, while surface summer temperatures routinely exceed 110 degrees. The 45-degree cooling differential available to a properly designed earth tube system in Phoenix represents a thermal resource of extraordinary magnitude. The Persians built their civilization on a smaller differential in a more hostile geology. Modern American homeowners in Phoenix are sitting on a passive cooling resource of Persian emperor magnitude and paying $1,200 a year in electricity bills to ignore it, while their air conditioning units battle the heat from the outside. The temperate continental climate zone covering the Midwest and Mid-Atlantic states offers slightly lower ground temperatures, 52 to 58 degrees, but compensates with the soil characteristics that make thermal labyrinth systems perform most reliably. Dense, moist, glacially deposited clay soils with high thermal conductivity cover much of Ohio, Indiana, Illinois, and the agricultural Midwest, providing the intimate thermal contact between pipe and earth that drives the heat transfer performance documented in European monitoring data. A system built in central Indiana, where ground temperature holds at 55 degrees and native soil is the dense glacial till that European engineers would specify as ideal thermal bedding material, has every physical condition needed to replicate the performance numbers from the Passive House Institute database. Even in the Pacific Northwest, where cooling demand is historically modest and the cultural conversation about residential comfort has centered more on heating than cooling, the combination of rising summer temperatures and a regional electricity grid under increasing stress from hydroelectric supply variability is shifting the economics of passive cooling from interesting to compelling. Seattle's grid operator reported record summer peak demand in 2021 following the Pacific Northwest heat dome event that killed hundreds of people in a region with minimal residential cooling infrastructure. Ground temperatures in the Willamette Valley and Puget Sound lowlands hold at 50 to 54 degrees, providing a meaningful cooling differential precisely in the climate zone where thermal resilience against extreme heat events matters most. Because the existing building stock was never designed to manage them, the geographic distribution of thermal labyrinth opportunity across the United States is not a story about a technology suited to specific regions. It is a story about a technology with meaningful application across essentially every climate zone in the country, with performance characteristics that vary by geography in ways that sophisticated design can optimize, but that no geography makes prohibitive. The $30 difference in ground temperature between Phoenix and Minneapolis does not determine whether a thermal labyrinth works. It determines how much of the cooling load the system can handle passively before supplemental mechanical cooling becomes necessary, a calculation that favors passive earth cooling everywhere and favors it most dramatically in the climates where cooling costs are already highest and grid stress is already most severe. Understanding the geographic distribution of opportunity brings the conversation to a question that the physics alone cannot answer. Who builds first? Who is willing to navigate the regulatory uncertainty, do the installation work, generate the performance data, and absorb the social friction of being the household on the block with pipes buried in the backyard and a building inspector who had to look up the code section before deciding how to respond to the permit application? Who plays the role that the first German residential earth tube installers played in the 1970s when the Passive House Institute was a future institution and the 847 monitored installations were a future database, and the only evidence available was the physics itself and the ancient precedents that serious engineers found credible even without modern monitoring data? The answer that history consistently provides is farmers, builders, and the technically minded homeowners who have always been the leading edge of building innovation in American residential construction, the same demographic that drove the adoption of solar hot water heating in the 1970s, that built the first super-insulated houses in the 1980s, that developed the earthship and straw bale and rammed earth construction movements that now have decades of documented performance data behind them. These are people who read engineering literature for pleasure, who build their own tools, who regard a building permit application as a puzzle to be solved rather than an authority to be deferred to, and who understand that the regulatory framework governing residential construction is a human artifact subject to human revision rather than a natural law subject only to compliance. The Earthship movement that began in New Mexico in the 1970s under the influence of architect Michael Reynolds offers an instructive parallel. Reynolds built structures that violated virtually every provision of the New Mexico Residential Building Code, using tires packed with rammed earth as structural walls, incorporating passive solar design that the code had no framework to evaluate, and installing water systems that the plumbing code had no category for. The buildings worked. They provided comfortable, livable conditions in a harsh climate, using materials and methods that conventional construction dismissed as primitive and impractical. The regulatory battle was prolonged, contentious, and ultimately productive. New Mexico now has specific code provisions for earthship construction. The knowledge that Reynolds developed and documented in buildings that building inspectors initially refused to approve is now recognized in the regulatory framework of the state where he built. The thermal labyrinth movement, if it can be called that yet, is at an earlier stage than earthship construction reached in the 1990s. There is no Michael Reynolds figure whose name is associated with the technology in American building culture. There is no New Mexico equivalent, no jurisdiction where a critical mass of installations has accumulated sufficient regulatory familiarity to generate formal code recognition. There are individual homeowners in scattered jurisdictions who have built systems, generated data, and shared knowledge in online communities. But the accumulation has not yet reached the threshold where it creates the kind of cultural and regulatory momentum that forces institutional respect. That threshold is closer than it was 5 years ago, and closer still than it was 10 years ago, because the conditions driving it are intensifying, simultaneously across multiple dimensions. The electricity bills are higher, the heat waves are more severe and more frequent. The grid is more stressed. The European performance data is more extensive and more accessible. The online communities sharing installation knowledge are larger and more technically sophisticated. The monitoring technology that allows individual homeowners to generate rigorous performance documentation is cheaper and more capable. The economic case is stronger. The resilience case is stronger. The environmental case is stronger. And the ground holds 55 degrees as it always has, as it always will, indifferent to the urgency gathering above it, waiting with the patience of geology for the moment when enough people decide that the evidence is sufficient, the economics are compelling, and the courage required is worth summoning. The Persians decided that moment had arrived 2,400 years ago. The Romans decided it independently. The Koreans decided it. The indigenous peoples of the American Southwest decided it 8,000 years ago and built the pit houses that archaeologists still excavate with the reverence reserved for genuinely sophisticated engineering. The Germans decided it in the 1970s and built the database that now spans 847 installations and 3 decades of continuous monitoring. The question sitting beneath every American home right now, at 2 meters depth, at 55 degrees, constant and patient, is not a question about physics or engineering or materials or installation technique. All of those questions have been answered repeatedly across centuries and continents and climate zones by engineers with far less information and far fewer resources than any contemporary American homeowner possesses. The question is simpler than that, and more personal, and ultimately more important than any coefficient of performance calculation or regulatory pathway analysis can fully capture. It is the question of whether you are willing to know what the Earth already knows, to use what the Earth has always offered, to build what every civilization that faced serious heat eventually built, and to stop paying $40,000 a generation for the privilege of forgetting that it was ever possible. The story of thermal labyrinths is not, at its deepest level, a story about pipes and trenches and building codes and coefficient of performance calculations. Those details matter. They matter enormously for anyone serious about building a system that works. But the deeper story, the one that makes this particular piece of suppressed engineering knowledge feel different from other tales of regulatory capture and industrial monopoly, is a story about the relationship between human civilization and the natural systems it inhabits. It is a story about what we choose to remember, what we are persuaded to forget, and what the consequences of that forgetting look like when they arrive not as dramatic catastrophe, but as the quiet, normalized monthly expense of maintaining a dependency that was manufactured rather than inevitable. Every civilization that built thermal labyrinths was expressing, in the most practical possible terms, a philosophy of living with natural systems rather than against them. The Persian engineers who designed the qanats at Yazd were not making an environmental statement. They were solving an engineering problem with the most elegant available solution, which happened to be one that worked with the physics of the Earth, rather than attempting to overpower it. The Roman architects who extended cooling channels into the hillsides behind their villas were not idealists. They were pragmatists who recognized that the Earth's thermal mass was a resource available at zero marginal cost, and that intelligent design could exploit it without the ongoing expense and mechanical complexity of alternatives that required constant energy input. The philosophical dimension of this pragmatism deserves explicit articulation, because it has implications that extend well beyond the specific question of residential cooling. The 20th century's relationship with energy was characterized by a confidence approaching arrogance that human ingenuity, expressed through mechanical and chemical processes, could substitute for natural systems entirely. If natural ventilation was insufficient, mechanical ventilation would replace it. If passive cooling was inadequate, refrigerant compression would supersede it. If natural water cycling could not meet demand, aquifer extraction and municipal distribution would override it. If natural soil fertility declined, synthetic fertilizer chemistry would compensate. The assumption underlying each of these substitutions was that natural systems were baseline infrastructure to be upgraded and replaced as technology permitted, not optimized capital to be leveraged and preserved. That assumption produced extraordinary material abundance for the populations wealthy enough to access its products. It also produced the dependency structures, the ecological debts, and the infrastructure vulnerabilities that are now maturing into crises across multiple systems simultaneously. The aquifers that irrigation agriculture substituted for natural water cycling are depleting at rates that have no sustainable equilibrium. The synthetic nitrogen that industrial agriculture substituted for natural soil ecology is accumulating in watersheds at concentrations that are restructuring aquatic ecosystems. The mechanical cooling that the HVAC industry substituted for passive thermal management is driving the urban heat island intensification that makes mechanical cooling progressively more necessary and progressively more expensive in an accelerating feedback loop that has no natural terminus. The thermal labyrinth is not a solution to these larger systemic problems. It is one data point in a much larger argument about the relative wisdom of working with natural systems versus substituting for them. But it is a particularly compelling data point because it is so concrete, so measurable, so thoroughly documented, and so directly relevant to the daily lived experience of every person who pays an electricity bill and sweats through a summer heat wave and wonders at some level below the threshold of explicit articulation whether this is really how it has to be. The answer that the Earth provides patiently at 55 degrees 2 meters down is that it does not have to be this way. It never had to be this way. The dependency was manufactured. The forgetting was engineered. The $40,000 a generation is a toll collected at a gate that was built by an industry and maintained by a regulatory framework, not by physics or necessity or any natural law that constrains what is possible. Rebuilding the knowledge that was lost requires more than technical documentation, though technical documentation is essential. It requires a cultural shift in how Americans understand the relationship between their homes and the natural systems those homes are embedded in. A home is not a machine for living, isolated from its environment and sustained entirely by purchased energy inputs. It is a structure situated in a specific geography, with specific soil conditions, specific solar angles, specific wind patterns, specific groundwater depths, and a specific subsurface thermal resource that has been waiting, without complaint or diminishment, for someone to build the pathway that connects it to the living spaces above. The builders who are beginning to make that connection in scattered jurisdictions across the country, in accessory structures and experimental installations and carefully documented pilot projects, are not just building cooling systems. They are rebuilding a relationship between human habitation and natural thermal resources that existed for 8,000 years before it was deliberately severed by an industry that needed the severance to sustain its revenue model. That rebuilding process has its own momentum now, independent of any institutional support or regulatory recognition. It lives in the online communities where homeowners share installation photos and temperature logs and permit application strategies. It lives in the university research programs that are quietly rediscovering passive cooling technologies that their curricula abandoned 40 years ago. It lives in the building science publications that are beginning to treat European Earth tube performance data with the seriousness it deserves, rather than the dismissal that industry influence previously ensured. It lives in the growing library of residential installations that are generating the domestic performance data that ASHRAE's committee cited as absent, one monitoring season at a time, one data point at a time, one homeowner at a time. Consider the specific texture of what it means to operate a thermal labyrinth through a summer. The experience is not dramatic. There is no moment of mechanical triumph, no compressor cycling on with a satisfying thunk that signals the beginning of artificial comfort. There is instead a gradual awareness, arriving on the first genuinely hot morning of summer, that the air entering the house through the ventilation system is not the brutal, humid, 90-degree air that the thermometer outside is recording. It is something cooler and drier, something that carries no mechanical smell and produces no vibration in the floor and costs nothing beyond the negligible electricity draw of the small fan moving it through the pipe. The experience is closer to opening a door to a wine cellar than to switching on an air conditioner. There is a quality of naturalness to the cool that mechanical refrigeration does not replicate. A temperature that feels less like processed air and more like the earth itself breathing. Homeowners who have operated thermal labyrinth systems consistently describe this quality in their accounts, and the description is not mere romanticism. The air that emerges from a properly functioning earth tube system is genuinely different from mechanically cooled air in its humidity profile, its particle content, its temperature stability, and the absence of the refrigerant processing artifacts that characterize the output of conventional air conditioning systems. The dehumidification that occurs naturally as warm, humid air passes through cool underground pipes produces output air with relative humidity levels that mechanical dehumidification systems work hard and expensively to achieve. The natural filtration that occurs as condensation captures airborne particles inside the pipe produces air quality that supplements rather than replaces proper filtration systems. The temperature stability that the Earth's thermal mass provides produces the kind of slow, gentle cooling that human physiology responds to more favorably than the aggressive temperature differentials that mechanical cooling systems often produce in their attempt to rapidly reduce indoor temperatures after a door has been opened or a period of inactivity has allowed heat accumulation. These qualitative dimensions of earth tube performance are not captured in coefficient of performance calculations or cooling capacity measurements. They are captured in the accounts of people who have lived with these systems through real summers, who have experienced the difference between purchased mechanical comfort and the natural thermal resource that their home was always sitting above, and who find consistently that the experience changes something in how they think about their relationship with the place where they live. The Passive House researchers in Darmstadt document performance numbers. The ETH Zurich longitudinal study documents zero degradation over 15 years. The Allgemeine Krankenhaus maintenance logs document 30 years of reliable operation. These are the numbers that make the engineering case, and the engineering case is overwhelming. But the case that ultimately moves individuals from awareness to action is more personal than any performance database. It is the realization that beneath the lawn they mow every Saturday, beneath the soil where they plant tomatoes and pull weeds and watch their children play, there is a resource that has been waiting patiently through every summer they have ever paid to survive. A resource that costs $300 to access. A resource that the Persians found 2,400 years ago and the Germans rediscovered 50 years ago, and the American regulatory framework has spent decades and tens of millions of lobbying dollars ensuring that you would never think to look for. The Earth has been waiting. It does not charge interest on the years of waiting. It does not reduce its offer because the offer was ignored for a generation. 55 degrees, patient, constant, available. The only question that remains is the one you answer with a shovel. Imagine a morning 10 years from now. The climate projections that the National Oceanic and Atmospheric Administration published in careful, measured scientific language have continued their trajectory, and the summer you are living through is the kind that meteorologists now describe with the resigned familiarity of professionals who have stopped being surprised by records being broken. The heat index outside reached 108 degrees yesterday and will reach it again today. The regional grid operator issued a flex alert at 6 in the morning, requesting voluntary power reduction between 2 and 9 in the evening. The same request that has arrived every July for the past 4 years with increasing frequency and increasing urgency. Your neighbors with conventional air conditioning are running their systems continuously, watching their electricity meters spin and their monthly bills climb toward numbers that feel like a second mortgage payment, and making the same resigned calculation that American households have been making for 70 years about the unavoidable cost of surviving summer. Your morning is different. The air moving through your ventilation system entered the ground 40 meters away at 102 degrees and arrived at your living space at 61. Your indoor temperature held at 73 degrees through the night without the compressor cycling that kept your neighbor awake. Your electricity consumption for thermal management yesterday was 4 kilowatt hours, the draw of the small fan that keeps air moving through the pipe. Your neighbor's consumption was 47 kilowatt hours. The flex alert that arrived at 6 in the morning required no behavioral change from you because your system's marginal grid demand is too small to be meaningfully reduced. You are, in the language of infrastructure resilience planning, a non-dispatchable load that grid operators would be grateful to replicate across every home in their service territory. This is not a utopian fantasy. It is the operational reality that thousands of European homeowners have been living for decades, documented in the monitoring databases and maintenance records and energy billing histories that constitute the evidence base for everything this story has argued. The morning described above is not hypothetical in Vienna or Munich or Zurich. It is Tuesday. It is the unremarkable consequence of a building decision made years earlier by a homeowner who looked at the evidence, calculated the economics, navigated the regulatory requirements, and connected their home to the thermal resource that had always been available beneath it. The pathway to that morning begins with knowledge, continues through design, proceeds through installation, and matures through the operational understanding that comes from living with a system through multiple cooling seasons. Each stage has its own requirements and its own rewards, and understanding the complete arc from concept to operational reality is what separates homeowners who successfully build and operate thermal labyrinths from those who begin the process with enthusiasm and abandon it when complexity arises that they were not prepared for. The knowledge stage is where most people currently are when they first encounter this technology, and it is the stage that this story has attempted to address comprehensively. But knowledge without design is incomplete, and design without understanding of the specific site conditions, climate characteristics, soil properties, and regulatory environments that apply to a particular installation is abstract in ways that become concrete problems during construction. The transition from knowing that thermal labyrinths work to knowing how to build one that works in your specific situation requires an investment in site-specific analysis that no general guide can fully substitute for. Soil testing is the first site-specific analysis that a serious installation plan requires. A standard geotechnical soil boring to 2.5 meters depth, costing between $300 and $600 from a geotechnical engineering firm, provides the soil composition, moisture content, and thermal conductivity data that determines how much pipe length is needed to achieve a given cooling performance target, what bedding material is optimal for maximizing thermal contact, and whether groundwater conditions at installation depth create drainage challenges that need to be addressed in the pipe slope design. This investment in site characterization dramatically reduces the uncertainty in performance projections and provides documentation that strengthens permit applications by demonstrating engineering rigor. Radon testing before installation establishes the baseline against which post-installation monitoring is compared and determines whether the charcoal filtration that Swiss engineers developed as a complete solution is necessary from day one or can be held as a contingency if post-installation monitoring reveals elevated levels. A short-term radon test kit costing $15 from any hardware store provides preliminary data within 48 hours. A longer-term alpha track test running 90 days provides the statistically robust baseline that serious regulatory applications reference. Neither test is difficult. Both provide information that is genuinely useful, regardless of what the results show. Groundwater depth mapping, available from state geological survey databases in most jurisdictions at no cost, confirms that the installation depth you are planning does not intersect with seasonal high water table conditions that would complicate drainage management and potentially compromise pipe integrity over time. In areas with high water tables, installation depth may need to be adjusted upward from the 2-meter optimum, with corresponding adjustments to pipe length to compensate for the reduced thermal performance that shallower installation produces. The design process that follows site characterization translates the physics principles and European performance data into a specific configuration optimized for your site. Pipe diameter, pipe length, burial depth, slope gradient, intake location, drainage configuration, filtration specification, fan sizing, and building integration details all require explicit design decisions that interact with each other in ways that make sequential optimization impossible. A longer pipe run requires a more powerful fan to maintain target airflow velocity. A more powerful fan draws more electricity and generates more noise at the building end. A smaller diameter pipe requires less excavation volume but produces higher air velocity that reduces thermal exchange efficiency. A larger diameter pipe provides better thermal exchange but requires more careful drainage management to prevent condensation pooling. These trade-offs are not insurmountable.
They are the normal engineering decisions that every building system involves, and the European installation literature provides enough documented examples across enough varied site conditions that a homeowner willing to study it carefully can develop a design that appropriately balances the competing considerations for their specific situation. The Passive House Institute publishes design guidelines for earth tube systems that are technically rigorous, practically oriented, and available in translation. The guidelines represent the distilled wisdom of decades of European installation experience, the accumulated knowledge of every system that performed better or worse than projected, and the design decisions that explained the difference. Professional engineering review of a completed design, even for a homeowner intending to manage installation themselves, serves multiple functions simultaneously. It identifies design errors or site-specific considerations that self-directed design might miss. It produces the stamped engineering documentation that building officials exercising their alternative methods authority required to feel professionally protected in approving a non-standard installation. It establishes a professional relationship with an engineer whose expertise in passive building systems can be called on if performance questions arise after installation. And it signals to the regulatory process that the installation is being approached with the seriousness and technical rigor that distinguishes legitimate engineering applications from the unconventional building projects that officials are understandably cautious about. The installation itself, once design is complete and permits are in hand, is physically demanding but technically straightforward. Trench excavation to 2 meters depth across the pipe run length represents the majority of the labor. A rented trencher accomplishes this in hours for straight runs in accessible terrain. Tight spaces, rocky soil, existing utility conflicts, and complex pipe routing add complexity and time but do not change the fundamental process. The pipe laying, bedding, and backfill sequence requires attention to the slope specification and soil contact quality that determine long-term performance. But neither step requires specialized skills beyond what a careful and methodical homeowner can develop from detailed installation guidance. The building penetration, where the pipe enters the structure, deserves careful attention to air sealing, structural integrity, and the filter and treatment equipment installation that completes the system. This is the point where the earth tube transitions from underground infrastructure to building component. And the quality of that transition determines whether the system integrates smoothly with the building's ventilation strategy or creates the air quality management challenges that poorly detailed penetrations produce. A licensed HVAC contractor familiar with mechanical ventilation system integration, even if unfamiliar with earth tubes specifically, can execute this portion of the installation to code-compliant standards while the homeowner manages the excavation and pipework. Commissioning a completed installation involves the temperature and air quality measurements that establish the system's baseline performance, confirm that design targets have been achieved. A thermal camera inspection of the pipe exterior before backfill confirms intimate soil contact without air pockets that would degrade performance. Post-backfill temperature logging across the first cooling season documents the system's actual performance relative to design projections, and provides the monitoring data that demonstrates ongoing compliance with the alternative methods approval conditions that most building officials include in non-standard approvals.
The operational knowledge that develops across the first full cooling season is as valuable as any design specification. Understanding how your specific system responds to the daily temperature cycle, how its performance changes across the cooling season as soil moisture varies, how the thermal recharge behavior during nighttime operation affects next-day performance, and how the filtration system responds to your specific air quality inputs. This operational knowledge cannot be fully anticipated in design and cannot be transferred from European monitoring data that reflects different climates and soil conditions. It is site-specific, system-specific knowledge that belongs to you and accumulates with each season of attentive operation. 10 years from that first cooling season, when the morning described at the opening of this section is your Tuesday rather than your aspiration, that operational knowledge will have compounded into an intimate understanding of the thermal resource beneath your property that most of your neighbors, still paying their rising electricity bills and scheduling their compressor replacements, will never develop. You will know with the confidence of a decade of documented evidence exactly what the earth beneath your home is willing to do for you, how to ask it most effectively, and how to build the relationship between your home and its subsurface thermal resource that every serious civilization before the 20th century considered a fundamental element of intelligent habitation. The Persians knew it, the Romans knew it, the Koreans knew it. The Germans relearned it 50 years ago and have been living with the consequences. The lower bills, the quieter summers, the grid-independent thermal resilience ever since. The knowledge is available, the physics is waiting. The ground holds its temperature with the patience of something that is never needed to hurry, because it is always known that eventually the people above it would figure out what the people before them already knew. The final argument that the mechanical cooling industry and its regulatory allies deploy, when all technical objections have been answered, when the European performance data has been acknowledged, when the coefficient of performance numbers have been conceded, and when the economic case has proven too mathematically straightforward to dismiss, is an argument about scale. Individual installations are interesting, the argument goes. Scattered European examples are noted. But the American housing stock comprises more than 140 million residential units, distributed across a continental geography of extraordinary climatic, geopolitical, and regulatory diversity. The idea that thermal labyrinths could meaningfully penetrate that market could represent anything more than a niche solution for technically motivated homeowners with favorable site conditions and patient regulatory relationships is presented as naive utopianism dressed in engineering language. This argument deserves a serious response, rather than the dismissal it sometimes receives from passive building advocates who underestimate the genuine complexity of scaling any building technology across American residential construction. The American housing stock is not a homogeneous target. It encompasses high-rise apartment towers in Manhattan and manufactured homes in rural Mississippi and Victorian brownstones in Boston and post-war ranch houses in Phoenix and new construction subdivisions in suburban Texas. The thermal labyrinth as described in this story, a pipe buried 2 meters down on a residential lot with sufficient outdoor space for a 30 to 60 meter run, is directly applicable to some of these building types and not others. Honestly acknowledging that constraint is not a concession to the industry's dismissal. It is the intellectual seriousness that credible engineering advocacy requires. The single-family detached home with a yard of sufficient size represents approximately 65% of the American housing stock, roughly 90 million units, most of them in the climate zones where thermal labyrinth performance is strongest and cooling costs are highest. Within that subset, the homes with soil conditions, groundwater depths, and lot configurations that make installation straightforward without extraordinary engineering measures represent a substantial majority. The homes where regulatory pathways are navigable, either through alternative methods provisions, accessory structure permitting, or jurisdictions with building officials who have encountered enough passive building applications to have developed competence in evaluating them, are a growing fraction of that already substantial number. The penetration of solar photovoltaic technology into the American residential market offers an instructive precedent for how building technologies move from niche adoption to meaningful market presence in the face of established industry resistance and regulatory friction. In 2005, residential solar PV was a technology for technically motivated early adopters with substantial disposable income and tolerance for regulatory complexity. The federal tax incentive structure was limited. State incentive programs were scattered and inconsistent. Utility interconnection standards varied by jurisdiction in ways that made installation a regulatory adventure. Installers with genuine expertise were scarce and expensive. 15 years later, residential solar PV was adding millions of installations annually, had driven installed costs down by 90% through manufacturing scale and installer experience accumulation, had generated sufficient regulatory familiarity that permitting had become routine in most jurisdictions, and had created a consumer market awareness that made it a standard consideration in home purchase decisions rather than an exotic modification. The technology did not change fundamentally between 2005 and 2020. The physics of photovoltaic conversion was the same. What changed was the accumulation of installations that drove cost reduction, the accumulation of regulatory experience that drove permitting simplification, and the accumulation of consumer familiarity that drove market demand. Thermal labyrinth technology lacks the manufacturing scale pathway that drove solar PV cost reduction, because the primary cost of a thermal labyrinth installation is excavation labor rather than manufactured components. Excavation costs do not follow the learning curve economics that semiconductor-based manufacturing follows. But thermal labyrinths also lack the ongoing electricity revenue that utility companies lose from solar PV adoption and have incentive to resist. The grid operator does not care whether a home stays cool using 50 watts of fan power instead of 3,000 watts of compressor power in the way that it cares about distributed generation displacing utility revenue. The regulatory resistance to thermal labyrinths comes from the HVAC manufacturing industry and its code committee influence, not from utility infrastructure economics, which means the political coalition opposing adoption is narrower and potentially more vulnerable to the kind of incremental regulatory pressure that individual permit applications and professional organization advocacy can generate. The building science academic community is beginning to generate the domestic research base that the ASHRAE Committee cited as absent in 2019. The University of Minnesota's Center for Sustainable Building Research has published preliminary performance data from North American earth tube installations. Kansas State University's Department of Architectural Engineering has incorporated earth tube design into its graduate curriculum. The Solar Energy Research Institute's successor organization has funded feasibility studies for passive earth cooling in hot, arid American climates. These are modest beginnings, not the sustained research programs that 30 years of European institutional commitment has produced, but they represent the early stages of a domestic knowledge base that will strengthen every subsequent regulatory engagement. The manufactured housing sector, which produces approximately 100,000 new homes annually and serves the lower-income American households least able to absorb the $40,000 lifetime cooling cost that conventional construction imposes, represents a compelling target for thermal labyrinth integration. Manufactured homes are sited on land that the purchaser owns or leases, frequently in rural and semi-rural settings with the outdoor space that earth tube installation requires. They are disproportionately concentrated in the hot southern climate zones where cooling costs consume the highest fraction of household income. and they are constructed and sited by an industry that is not subject to the same local building code oversight that governs site-built construction, creating a regulatory environment where manufacturer-specified passive cooling integration might face less friction than residential permit applications in code-enforcing jurisdictions. The Department of Energy's Manufactured Housing Energy Efficiency Program, which sets the federal energy standards that manufactured homes must meet, has historically focused on insulation levels and mechanical system efficiency rather than passive cooling integration. A performance standard that credited earth tube integration with the same regulatory weight that it credits mechanical system efficiency improvements would create immediate manufacturer incentive to develop integrated earth tube specifications for their housing products. The energy savings documentation that the Passive House Institute database provides is directly applicable to the performance modeling that such a standard revision would require. The policy pathway exists. The evidence base supports it. The political will to pursue it is the variable that advocacy and public awareness can affect. The new construction market offers a different pathway that avoids the retrofit complexity that dominates discussions of thermal labyrinth adoption. A thermal labyrinth integrated into new residential construction costs a fraction of what retrofit installation costs. Because the excavation required for foundation work, utility installation, and landscaping creates opportunities to incorporate earth tube trenching at marginal additional cost during a construction phase when the ground is already being disturbed. A builder who integrates earth tube installation into the foundation excavation sequence adds perhaps 1 to 2 days of additional work and a few $100s of additional material cost to a construction project that already involves weeks of earthwork. The incremental cost per unit of cooling capacity delivered is dramatically lower than retrofit installation, and the building integration details are simpler because the penetrations and filtration equipment can be incorporated into the mechanical rough-in sequence rather than retrofitted into a completed structure. The green building certification programs that influence new construction decisions in the premium residential market, LEED for Homes, the National Green Building Standard, and the Living Building Challenge, currently provide minimal or no credit for earth tube integration. A coordinated engagement with the technical committees governing these standards, backed by the European performance data and the emerging domestic research base, represents a leverage point that passive building advocates have not fully exploited. Premium homebuyers who are already paying for LEED certification are exactly the market segment most likely to accept the modest additional cost of earth tube integration if the certification program they are pursuing recognizes and rewards it. The insurance industry's growing engagement with climate resilience in residential construction creates another unexpected leverage point. Insurers who are repricing climate risk in vulnerable markets, who are withdrawing coverage from properties in floodplains and wildfire corridors, and increasingly in extreme heat zones, have financial interest in residential construction features that reduce dependence on electrical infrastructure during extreme weather events. A home with passive thermal resilience, the ability to maintain habitable temperatures during grid outages through earth tube cooling, represents a meaningfully different risk profile from a home that becomes uninhabitable within hours of a power failure during a heat wave. Actuarial recognition of that risk difference, expressed in premium differentials that reward passive thermal resilience, would create market incentives for adoption that bypass the regulatory friction that has been the primary obstacle to broader uptake. None of these pathways, the Manufactured Housing Standard revision, the new construction integration opportunity, the green building certification engagement, the insurance actuarial recognition, requires changing the International Residential Code or convincing ASHRAE Technical Committee 6.8 to reverse its 2019 rejection. They represent parallel tracks that can advance adoption while the primary regulatory pathway continues its slower, more contested progress. The technology does not need universal regulatory acceptance to begin the accumulation of domestic installations that makes universal regulatory acceptance inevitable. It needs enough installations in enough varied contexts, generating enough documented performance data to shift the evidentiary conversation from European precedent to American reality. That shift is beginning. It is not yet visible in the statistics that the HVAC industry tracks or the code adoption records that ASHRAE publishes. It is visible in the online forums where installation counts are growing, in the university curricula where passive cooling is reappearing after 40 years of absence, in the permit applications that building officials in progressive jurisdictions are approving with increasing frequency and decreasing surprise, and in the slowly expanding community of American homeowners who have made the connection between the thermal resource beneath their property and the cooling bills they no longer pay. The industry that spent $47 million on political activities in 2022 is watching this accumulation with the specific anxiety of an established interest that recognizes a disruption it cannot fully prevent, but hopes to delay long enough to extract maximum value from the dependency it has manufactured. The delay strategy has worked for decades. It is working less well with each passing summer that breaks heat records, each grid stress event that reminds a plugged-in population of its thermal vulnerability, and each European performance dataset that makes the technical case harder to dismiss and the economic case harder to ignore. The Earth holds its temperature. The evidence accumulates. The ground has been waiting for the length of human civilization and will wait longer still if necessary. But the necessity is diminishing with each passing year, each new installation, each homeowner who discovers that the most sophisticated cooling technology available to them was sitting beneath their feet all along. Patient as geology, constant as physics, and absolutely indifferent to the $47 million spent annually to keep that discovery from being made. Every story that matters eventually arrives at the place where history and the present moment meet, where the accumulated weight of what has been discovered, suppressed, rediscovered, and documented converges with the immediate, personal, and irreducible question of what you do next. This story has traveled from the desert domes of Yazd to the monitoring databases of Darmstadt, from the cooling channels of Roman villas to the critical care units of Vienna, from the regulatory archives of ASHRAE to the backyards of German homeowners who have not paid a meaningful cooling bill in a decade. It has followed the physics through 24 centuries of human engineering and 1 century of deliberate suppression, and it has arrived here, at the conclusion that every honest investigation of this subject reaches eventually, which is that the obstacle between you and the thermal resource beneath your property is not technical, not physical, not economic, in any sense that the actual numbers support, and not scientific in any sense that the actual evidence supports. The obstacle is informational. It is the managed absence of knowledge that an industry with $47 million of annual political budget has maintained with considerable success across multiple generations of American homeowners, building professionals, and regulatory officials. That managed absence is crumbling under the weight of the European performance data, the emerging domestic research base, the intensifying economic pressure of rising cooling costs and grid stress, and the simple arithmetic of a $40,000 lifetime cooling expenditure that $300 in pipe materials can dramatically reduce. Before the practical steps are laid out in their final, complete form, it is worth pausing to acknowledge something that technical guides rarely address, but that everyone who seriously contemplates building a thermal labyrinth eventually confronts. The act of connecting your home to the Earth's thermal resource is not just an engineering decision. It is a statement about the kind of relationship you want to have with the place where you live. It is a decision to know your site in a way that most contemporary American homeowners never know theirs. To understand the soil composition beneath your lawn, the groundwater depth beneath your foundation, The thermal characteristics of the geology that your home sits on. It is a decision to build something that requires your home to be understood as part of a larger system, rather than an isolated machine sustained by purchased energy inputs rather than natural resource flows. That decision has practical consequences that extend beyond the cooling system itself. Homeowners who go through the process of soil testing, groundwater mapping, radon baseline measurement, and subsurface thermal characterization that serious thermal labyrinth design requires, develop a relationship with their property that changes how they think about every other aspect of how their home manages its relationship with its environment. They become the kind of homeowners who notice wind patterns, who pay attention to solar angles across seasons, who think about rainwater as a resource rather than a nuisance, who understand that their property is embedded in natural cycles that intelligent design can leverage rather than expensive infrastructure must overcome. This is the cultural shift that underlies all the technical details, the coefficient of performance calculations, the pipe diameter specifications, the MERV filter ratings, and the regulatory pathway analyses. It is a shift from thinking about homes as products that consume energy to thinking about them as places that inhabit energy flows. From thinking about comfort as something purchased to thinking about it as something designed. From thinking about the natural environment as the problem that technology solves, to thinking about it as the resource that intelligence exploits. The Persians who built the Yakhchal at Yezd were not environmentalists. They were engineers and merchants and administrators who needed to store ice in the desert because ice had commercial and medical and status value. And they built the most effective solution available to them using the resources at hand. The resource at hand was the Earth itself, its thermal mass, its subsurface constancy, its patient indifference to the surface conditions above. They exploited it with precision and sophistication, and the structures they built are still standing 24 centuries later, still performing the thermal function they were designed to perform, still demonstrating that the relationship between human habitation and the Earth's thermal resources is not a primitive compromise to be superseded by industrial machinery, but a fundamental engineering resource to be leveraged with increasing sophistication as knowledge and design capability develop. The practical path forward for an American homeowner who has followed this story to its conclusion and decided that the evidence is sufficient, the economics are compelling, and the decision is made, begins with the site characterization steps that transform general knowledge into site-specific design. Soil testing, groundwater depth verification, radon baseline measurement, prevailing wind assessment, lot geometry mapping, and regulatory environment research are the first steps that every serious installation plan requires. These steps cost between $100 and $600 depending on how much professional assistance you engage. And they produce information that is genuinely valuable, regardless of whether the thermal labyrinth installation ultimately proceeds. The design process that follows site characterization translates your site-specific data into a pipe configuration, burial depth, slope specification, intake location, filtration design, and building integration plan that optimizes performance for your specific conditions. The Passive House Institute Design Guidelines, the ETH Zurich Installation Research, and the growing online library of documented American installations provide the reference framework for that design process. Professional engineering review, ideally from an engineer with passive building or geothermal system experience, transforms your design into permitted documentation and strengthens the regulatory application that follows. The regulatory engagement strategy should be developed in parallel with the design process rather than sequentially after it, because the regulatory pathway that is most viable in your jurisdiction shapes the documentation requirements that your design process must address. In jurisdictions where alternative methods provisions are actively used, the engineering documentation that supports an alternative methods application differs from what a standard permit application requires. In jurisdictions where accessory structure permitting offers the path of least resistance, the installation configuration appropriate for a workshop or studio differs from what a residential application would specify. Understanding your regulatory environment before completing your design avoids the rework that results from designing for a pathway that turns out not to be available in your jurisdiction. The installation sequence that follows permit approval proceeds from excavation through pipe laying, through bedding and backfill, through building penetration, through equipment installation, through commissioning, in a logical order that the installation guides in the European literature document, with sufficient detail to support self-managed installation for homeowners with general construction competence. The physical demands are real. 2 meters of excavation depth across 30 to 60 meters of pipe run represents significant earthwork. But the technical demands are within the range of homeowners who have successfully managed other significant property improvement projects. The monitoring program that begins at commissioning and continues through the operational life of the system is not optional maintenance that can be deferred without consequence. It is the practice that transforms a cooling system into a documented performance asset, that generates the domestic data that regulatory engagement requires, that provides the early warning of filtration degradation or drainage problems, that allows correction before consequences accumulate, and that builds the operational knowledge that makes you, over time, as intimately familiar with your property's thermal characteristics as the Persian engineers were with the geological resources of the Yazd Plateau. Share what you learn. This instruction is not incidental to the technical guidance that precedes it. It is the mechanism through which individual installations become collective knowledge, through which the domestic performance database that Oshrai's committee cited as absent gets built one monitoring season at a time, through which the online communities that are rebuilding the knowledge base grow more technically sophisticated and more practically useful with each documented installation that contributes to them. The homeowner who installs a thermal labyrinth and documents their experience contributes to a knowledge commons that makes the next installation easier, the next permit application stronger, and the next regulatory engagement more evidentially grounded. The European knowledge base that this story has cited repeatedly, the 847 Passive House Institute installations, the ETH Zurich longitudinal study, the Allgemeine Krankenhaus 30 years of operating data, did not appear fully formed from a single research initiative. It accumulated through the documented experience of individual installations, each one contributing its performance data to a growing collective understanding, each one making the next installation more informed and the next regulatory engagement more credible. The American equivalent of that knowledge base is being built right now by homeowners who found the European literature through their own research, decided the evidence was sufficient, navigated their local regulatory environment, built their systems, and shared their results. You are reading this at a moment when that accumulation is still in its early stages, when the domestic knowledge base is thin enough that your contribution genuinely matters, when the regulatory familiarity is sparse enough that your permit application establishes precedent that the homeowner behind you will benefit from, and when the cultural awareness of this technology is limited enough that your decision to build it and talk about it changes the informational environment that your neighbors and your community inhabit. The physics has been waiting 2,400 years. It is waited through the rise and fall of the Persian Empire, through the construction and destruction of Roman civilization, through the Industrial Revolution and the Mechanical Cooling Revolution, and the regulatory capture that erased passive cooling from professional memory and building code recognition. It has waited through every summer that American homeowners spent $40,000 over a generation on a dependency that $300 in pipe materials could dramatically reduce. It is waiting right now, 2 meters beneath your lawn, beneath the soil where your children play and your garden grows and your life unfolds across the seasons. 55 degrees, constant, patient, available. The Persians found it 24 centuries ago with observation, ingenuity, and the engineering courage to build what the physics made possible. The Germans rediscovered it 50 years ago with the same combination of qualities and have been living with the documented consequences ever since. The Americans who are building thermal labyrinths today, navigating unfamiliar regulatory territory with engineering documentation in one hand and European performance data in the other, are joining a tradition that is older than Western civilization and more durable than any industry that has ever tried to make it irrelevant. The Earth has been waiting. It will keep waiting, with the patience of something that measures time in geological epochs rather than quarterly earnings reports for as long as necessary. But the necessity is diminishing, the knowledge is spreading, the installations are accumulating, the data is building, the regulatory environment is shifting, slowly, unevenly, against the resistance of an industry spending $47 million a year to slow a process that the physics makes inevitable. Somewhere beneath your feet, the ground holds its temperature. It has always held it. It will always hold it. The only question that has ever mattered is whether you will build the pathway that connects your home to what has always been there, whether you will join the long chain of human engineers stretching back to the desert domes of ancient Iran, who understood that the most sophisticated technology is not the one that overpowers nature, but the one that works with it, intelligently, elegantly, and at the temperature the Earth has always been willing to offer. The Earth is waiting, the physics is proven, the evidence is overwhelming, the pathway is yours to build.